Hello there, and welcome to Physics with William, where difficult ideas are allowed to slow down, loosen their collars, and make themselves comfortable enough to be understood without any unnecessary rushing about. Tonight we are settling in with one of the most stubborn questions in all of physics, a question that sounds as though it ought to have been answered cleanly and confidently by now, filed away in a tidy drawer and never troubled us again. And yet it remains, still sitting at the centre of modern science with the calm expression of something that knows perfectly well it cannot be pinned down. Is light a wave or a particle? Is matter a wave or a particle? And why, after more than a century of some of the brightest minds ever to stare at reality until their tea went cold, do we still not have an answer that feels fully satisfying? Before we get too far into that, I would love to know where in the world you're listening from tonight and what sort of hour has found you. Is it late and quiet where you are? Have the streets gone soft and empty? Are you listening under a blanket, on a train, in bed, or in that slightly uncomfortable chair you promised yourself you would replace months ago? There is something fitting, I think, about hearing a story like this from wherever you happen to be, because the question itself is all about what it means to look at something and what changes when you do. If you find this kind of slow wandering through physics soothing, or interesting, or simply a gentler way to wind down than scrolling yourself into a state of mild confusion, I would be very grateful if you liked the video and subscribed. It helps this little corner of quiet science find the people who might enjoy it, or at least the people who are willing to forgive me for making their bedtime more complicated with quantum mechanics. Now, this is one of those topics that sounds at first like it should be simple. Waves and particles seem like very ordinary things. Waves are familiar. You have seen water ripple across a pond when a stone lands in it. You have watched the sea roll toward the shore in lines and curls and bursts of foam. You have heard sound waves without ever needing to think much about them. A wave spreads out. It has a rhythm. It can overlap with other waves. It can reinforce or cancel. It does not usually sit politely in one tiny place and stay there like a well-behaved pebble. Particles also feel familiar. A grain of sand is a particle. A speck of dust drifting through a shaft of sunlight is a particle. A raindrop, a bead, a seed, a crumb on the table you swear came from nowhere. A particle is the kind of thing that seems to be somewhere definite. It might move around, certainly, but at any given moment you imagine it having a location. It is this thing, here, doing that. It may be small, but it is still in spirit a little object. For a long time, physics was perfectly comfortable with this division. Waves were waves. Particles were particles. There might be some messy edge cases in the world, but the categories themselves seemed solid enough. If you were studying light, you tried to decide which side it belonged on. If you were studying matter, you felt fairly confident that matter, being made of stuff, belonged on the particle side and could get on with your day. This confidence, as it turns out, was a little premature. The trouble begins when nature refuses to respect the neat labels we give it. Physics has always had this habit of allowing us just enough certainty to become smug, and then introducing an experiment that makes the entire picture wobble. Light was one of the earliest offenders. In some situations, light looked very much like a wave. It spread out. It bent around obstacles. It produced patterns of interference, the sort of thing waves do when they overlap. Two waves can combine so that their peaks line up and make a stronger wave, or their peak and trough meet and partially cancel each other. Light seemed capable of exactly that kind of behaviour. That was a strong point in favour of light being a wave, and for a while many physicists were quite happy with that conclusion. Then came other results. In some experiments, light behaved not like a smooth spread-out wave, but as if it arrived in tiny separate packets, little bursts that struck matter in discrete individual events. It did not seem to smear itself continuously across an interaction. It seemed to come in countable doses. That is much more particle-like. One can almost hear the sighs beginning around the laboratories of Europe. If light was a wave, why did it sometimes act like a shower of tiny little hits? If it was a particle, why could it interfere with itself like something spread out? And matters became worse, because once physicists had finished being thoroughly unsettled by light, they discovered that electrons, which had seemed comfortably particle-like, could also produce wave-style interference under the right conditions. Electrons, those tiny bits of matter that help make up atoms and electricity, and much of the ordinary stuff around you did not stay in their assigned category either. They too could act in ways that sounded suspiciously wave-like, until the moment you looked for a definite outcome, at which point they offered one. It was as though the universe had taken two boxes labelled wave and particle, emptied them onto the floor, mixed the contents thoroughly, and then quietly left the room. That is the central puzzle we're beginning with tonight. Not merely that physicists had trouble deciding what light and matter were, but that the question itself may be built in the wrong way. When we ask whether something is a wave or a particle, we imagine nature owes us a choice between two familiar pictures. But quantum physics suggests something much stranger. It suggests that wave and particle are not deep identities hiding inside things. They are limited human descriptions. They are models that work in some situations and fail in others. Useful, yes. Final, no. This is where the topic becomes genuinely unsettling in a way that reaches beyond science and into ordinary thought. Because most of us are used to assuming that the world has clear properties waiting there to be discovered. A chair is a chair whether or not you look at it. A coin on the table has a location whether or not anyone is paying attention. A train either has arrived or it has not, though in fairness, railway schedules sometimes test this principle. We tend to imagine that observation is passive. We look, and the world simply reveals what was already the case. Quantum physics puts pressure on that assumption. It does not say that human thoughts magically control reality, which would make every grocery trip far too exciting, but it does say that how a system is measured matters deeply to what kind of behaviour becomes visible. The setup of the experiment is not just a window onto reality. It is part of the story. Ask one kind of question, and you get something that fits the language of waves. Ask another, and you get something that looks like a particle. Try to insist that one of those answers must be the full truth in all circumstances, and the world stops cooperating. It is very tempting at this stage to try to calm ourselves with metaphor. Perhaps one might say light is both a wave and a particle at once, and there is some usefulness in that phrase. But it can also mislead. It suggests two complete identities stacked together, as though a thing were wearing two hats at the same time. Quantum theory points somewhere subtler than that. The wave part in the modern view is not exactly a little water ripple hidden inside an electron. It is not a wave made of ordinary stuff sloshing through space. It is more like a mathematical description of possibilities, of where something might be found and with what likelihood certain outcomes may occur. And then when a measurement is made, one actual definite result appears. Not a little cloud of maybes forever. One result. This is one of the reasons the subject has such staying power. It is not merely technically strange. It pokes at the habits of thought we use every day. We are creatures who like nouns. We like to say what something is. We like categories because they let us feel the world is under control. Dog, table, river, rain, wave, particle. The labels help us move through life without needing to reinvent language every morning. Quantum objects do not always honour that arrangement. They are not being difficult for the sake of it. They are simply not shaped to fit the boxes our common sense built out of everyday experience. That everyday experience, it must be said, is not a universal guide to reality. It is a local convenience developed by brains that evolved to throw sticks, judge distances, avoid danger, and locate snacks. Common sense is very good at dealing with medium-sized objects moving at ordinary speeds. It helps you cross the road and pour tea without existential collapse. But it is not automatically trustworthy at the scale of atoms and light. The world down there is not obliged to resemble the world of pebbles and waves on a beach, simply because that is what we find intuitive. Nature did not hold a meeting and ask us what kind of behaviour would feel reasonable. Still, one can sympathise with the physicists who struggled with all this. because the problem did not arrive as a grand philosophical statement. It came in pieces through experiments, each one refusing to be dismissed. And that is an important point. Quantum mechanics was not invented because scientists fancied making life confusing for students. It was forced into being by evidence. Again and again, experiments showed that the old pictures were not enough. Light could not be treated only as a wave. Matter could not be treated only as a collection of tiny billiard balls. Something deeper was going on, something that required a new framework. The funny thing is that physics is often at its most honest when it sounds least comfortable. A less honest science might have insisted on certainty when none was available. It might have hidden the awkward bits under confident language and pretended the categories were still intact. Physics at its best does the opposite. It says, here is what we can predict, here is what we can measure, and here is where our ordinary words begin to fail us. That failure is not weakness. In a strange way, it is progress. It means we have pushed our understanding far enough that the old language no longer stretches to cover what we have found. So tonight, and over the course of this journey, we are going to take our time with that failure and see what it teaches us. We will look at the older classical picture in which waves and particles seemed separate and sensible. We will see why waves once looked like the obvious explanation for light, and why particles came roaring back into the conversation. We will spend time with the famous double-slit experiment, that elegant little machine for causing intellectual unease. We will watch electrons and light behave in ways that seem almost designed to irritate anyone who insists on plain answers, and slowly, without making the mistake of rushing toward a tidy slogan, we will try to understand what the quantum view is really telling us. Because the goal here is not to collect clever phrases about mystery, it is to see precisely where the mystery comes from. There is a big difference between saying quantum physics is weird and understanding why it had to become weird. The first is a mood, the second is knowledge, and if possible I would like us to aim for the second without entirely losing the first, because the sense of strangeness is part of the point. Not all of reality was built for our comfort. Consider for a moment how much easier the story would be if the answer really were simple. Imagine if light had turned out to be only a wave, no exceptions, and electrons only particles, no complications. Textbooks would be shorter. Philosophy departments would lose several favourite arguments. Countless late-night videos like this one would have to find some other topic on which to gently unsettle you. But the universe had other plans. It gave us a world in which the behaviour of things depends in a profound way on how they are probed. It gave us a formalism that predicts outcomes with astonishing accuracy, while still leaving us arguing over what those predictions mean. It gave us, in other words, not ignorance, but a very sophisticated form of partial understanding. That phrase may sound disappointing at first, but partial understanding is in fact one of science's greatest achievements. We sometimes imagine that real knowledge must come as a final answer, something hard and complete. Yet much of powerful science consists not in possessing ultimate pictures, but in building models that capture what can be observed and predicted. Quantum mechanics does that extremely well. It tells us how probabilities evolve, what measurements are likely to yield, how atoms behave, how semiconductors work, why chemistry has the structure it does, why stars shine as they do, why modern electronics are even possible. This is not a shaky theory held together with hopeful string. It is one of the most successful frameworks in all of science. And yet when we ask it, in plain language, so what is the electron really? It becomes far less willing to speak in the terms we prefer. There is something almost humbling about that. We can build devices based on quantum rules. We can calculate outcomes with astonishing precision. We can manipulate quantum behaviour in laboratories and technologies. And still, when we reach for the familiar categories of everyday thought, the thing itself slips sideways. Not because it is unreal, but because our mental furniture was arranged for a different scale of existence. If that sounds a little frustrating, I think that is fair. It was frustrating to many of the physicists who helped create quantum theory. Some embraced the new picture more readily than others. Some treated the mathematics as the main thing and warned against demanding a hidden visual story behind it. Others felt strongly that a deeper explanation must still exist, one that would restore a more intuitive reality underneath the probabilities. Those debates have never entirely gone away. Even now, physicists and philosophers continue to argue over interpretation, over what the theory is saying about the world and not merely what it lets us calculate. So when we ask whether physics can answer the question wave or particle, the honest reply is not that physics has failed completely. It is that physics has outgrown the question as it was originally framed. This opening stretch of the story matters because it sets the tone for everything that follows. We're not walking into a neat detective mystery where the clues line up and the culprit confesses. We're walking into a case where the clues themselves transform the question. At first glance, it seems we're trying to determine whether light and matter belong in one category or another. Soon enough, we realise the categories were built from the wrong starting assumptions. And after that, the real work begins. Because now we have to understand what quantum theory offers in place of the old certainty. That replacement is not nonsense. It is not magic. It is not a license to say that anything can happen, or that reality is made of wishes and vibes and late evening confusion. Quite the opposite. Quantum mechanics is disciplined and exacting. It places sharp limits on what can be said, and it demands care in how one says it. The difficulty is that its discipline does not line up with the habits of ordinary language. It requires us to speak more carefully than common sense usually demands. It asks us to stop treating wave and particle as tiny identity cards, and start treating them as context-dependent ways of describing different aspects of quantum behaviour. That might sound like a small adjustment, but it changes a great deal. It means that when light interferes, we should not rush to imagine it secretly becoming a tiny ocean swell. When an electron lands as a single localized hit on a detector, we should not rush to imagine it was simply a microscopic pebble all along. Both images contain something useful. Neither is the whole story. Reality at the quantum level appears to be deeper than either picture on its own, and perhaps that is where the subject becomes quietly beautiful, though I promise not to get too misty-eyed about it. Physics here is not merely finding odd facts, it is teaching restraint. It is reminding us that the first categories we learn from everyday life may not be the final categories of nature. The universe is under no obligation to keep its deepest workings within the comfort zone of our ancestors, who, admirable as they were, did not spend much time building double-slit apparatus in caves. We inherit language shaped by ordinary objects, and then science invites us to push beyond it. So as we move forward, let us keep the basic question in view without clinging too tightly to its original form: wave or particle? It is a good question to begin with because it captures exactly the kind of split that classical physics expected. It is also a question quantum physics slowly dismantles. By the time we're done, the real lesson will not be that light and matter are indecisive. It will be that our labels are smaller than the world they try to describe, and that brings us naturally to the older world picture that made the whole problem possible in the first place. Because before quantum theory complicated everything, waves and particles each had their own clear territory, their own behaviour, and their own quiet claim to common sense. Once you see how solid that older division once seemed, it becomes much easier to understand why the experiments that challenged it caused such a shock, and why physicists found themselves having to rethink not just light, but the very terms in which reality was described. To understand why the question of wave or particle became such a problem later on, it helps to spend a little time in the older world of physics, back when the wave picture seemed not only sensible, but almost unbeatable. There was a period when waves appeared to offer exactly the kind of explanation science likes most. They were elegant, flexible, mathematically rich, and supported by a growing number of experiments. If you had walked into the scientific conversation during that era, you would have been forgiven for thinking the case was nearly closed. Light, many believed, was a wave, not metaphorically, not approximately, but in the same broad sense that sound is a wave and ripples on water are waves. The world looked as though it had finally yielded one of its secrets in a form both graceful and satisfying. That confidence did not appear out of nowhere. It rested on a long habit of watching how disturbances move through the world. Waves are, in many ways, among the most intuitive patterns in nature once you start paying attention to them. Drop a stone into a pond and rings spread outward. Pluck a string and a vibration travels along it. Clap your hands in a large room and the pressure change moves through the air until it reaches someone else's sound. Even before the mathematics became sophisticated, people could see that waves had a distinctive style. They spread, they overlap, they bend around obstacles, they can be reflected, they can be focused, they can fade, reinforce, and interfere. Once you get used to noticing them, they seem to turn up everywhere as though nature simply enjoys a good ripple. This made the idea of light as a wave attractive for reasons deeper than fashion. It offered a way of placing light into a family of known behaviours. Rather than treating light as some mysterious special thing, the wave picture suggested it belonged to a broader class of phenomena. And science is always pleased when something strange can be made less strange by showing that it follows a pattern already seen elsewhere. To explain one puzzling thing by connecting it to many familiar things is a kind of intellectual economy. It reduces the number of separate mysteries lying around the universe, which physicists generally prefer, especially if they have other mysteries already taking up space on the desk. In the early debates about light, there have been competing ideas. Some thinkers imagined light as a stream of tiny particles emitted by luminous bodies. Others suspected it behaved more like a wave. Neither side was being foolish. Both were trying to account for what was visible. Light travels in straight lines most of the time, which makes it easy to think of it as something like little projectiles. It also reflects cleanly from mirrors and bends when passing into water or glass, which can be described in different ways depending on the model you favour. At first, the evidence did not force an immediate surrender from either camp, but waves have a remarkable advantage when it comes to explaining certain kinds of behaviour. If a wave passes through a narrow opening, it does not simply continue in a rigid straight line as though nothing happened. It spreads out. If two waves meet, they do not crash into each other and stop like clumsy carts in a narrow street. They overlap. In some places they add together, in others they cancel. This phenomenon of interference turned out to be one of the great clues. It suggested that if light could be shown to produce clear interference patterns, then the wave picture would gain serious strength. Because interference is one of those things waves do naturally and particles do not, at least not in any ordinary classical sense. This is where the scientific mood began to shift in a decisive way. Experiments with light revealed patterns that looked deeply wave-like. When light passed through narrow slits or edges, it did not always behave as though made of neat, independent rays marching forward with military discipline. Instead, it spread and produced fringes of brightness and darkness. These bright and dark bands were not random. They were structured, regular, and exactly the sort of thing one expects if different parts of a wave arrive together and either reinforce or cancel each other. A bright band appears where the wave contributions line up well. A dark band appears where they oppose each other. It was hard to look at these results and not feel the pull of the wave idea. One of the most important figures in building this case was Christian Huygens, who proposed that light could be understood in terms of wavefronts spreading through space. His way of thinking was beautifully simple. Every point on a wavefront could be treated as a source of new little wavelets, and the advancing front of the wave could be understood from how these combine. That idea helped explain reflection and refraction in a way that was not only clever but visually intuitive. It gave physicists a method, not just a slogan, and that matters. Science does not thrive on labels alone. It thrives when a label comes with a framework that generates predictions. Still, it was not only theoretical neatness that made the wave picture powerful. It was experiment after experiment adding weight to the same side of the scale. Thomas Young in the early 19th century performed the famous double-slit experiment with light, and the results were hard to ignore. When light passed through two narrow slits, The pattern on the screen beyond did not look like two simple bright patches corresponding to two little streams of particles. It looked like an interference pattern, a series of alternating bands that made far more sense if light was spreading as a wave from each slit and those waves were combining. This was the sort of result that makes a scientific model suddenly feel not just plausible, but compelling. The wave theory gained even more force through the work of Augustin Fresnel, who developed it mathematically and showed that the strange details of diffraction and interference could be handled with impressive accuracy. There is something deeply persuasive about a theory that can not only tell a story, but calculate the details. Once you can predict where bright and dark bands will fall, once you can explain subtle optical effects that once seemed puzzling, confidence grows. The wave view of light was no longer a vague analogy to water ripples. It was becoming a full scientific account with structure, precision, and reach. Then came another crucial piece of evidence, and with it an important refinement. Light turned out to show polarization. Now, without getting tangled in too much technical language too soon, polarization revealed something about the direction in which the oscillation associated with light takes place. This mattered because not all waves are alike. Sound in air is a longitudinal wave, meaning the disturbance runs along the same direction the wave travels, like regions of compression and rarefaction moving through the medium. But polarization suggested that light behaved more like a transverse wave, with the oscillation happening across the direction of travel. That might sound like a small detail, but in science small details often decide the matter. Polarization strengthened the case that light was indeed wave-like, but not like sound. It belonged to a different wave family. At this stage, the wave picture was doing extremely well. It explained interference, it explained diffraction, it handled reflection and refraction. It incorporated polarization. It offered a coherent framework that tied many optical phenomena together under one roof. You can see why the scientific world began to feel that waves were ruling the matter of light. The particle idea, though not entirely forgotten, started to look old-fashioned, like an explanation from an earlier stage of the story that had now been superseded by something more subtle and more complete. And then, in the 19th century, the wave triumph became grander still. This is where James Clerk Maxwell entered the picture and turned the theory of light from a successful optical model into something far more ambitious. Maxwell was working on electricity and magnetism, two phenomena that had seemed related in suggestive ways. Through a remarkable synthesis, he developed a unified theory showing that changing electric fields and changing magnetic fields could generate each other and propagate through space as waves. When he calculated the speed of these electromagnetic waves, it matched the known speed of light. That was one of those moments in science that feels almost theatrical in retrospect. The numbers lined up, the pieces clicked. Light, it appeared, was an electromagnetic wave. That conclusion was so powerful because it did more than explain old facts. It connected entire domains of physics. Light was no longer just a topic in optics. It became part of the broader structure of electromagnetism. It sat inside a theory of extraordinary reach and beauty, a theory that not only described visible light, but implied the existence of other electromagnetic waves beyond what the eye can see. Radio waves, microwaves, infrared, ultraviolet, all could be understood as variations within the same family. A single framework suddenly covered a vast range of phenomena. This is exactly the kind of success that makes scientists fall a little in love with a theory, and not without reason. When a theory starts linking fields that once seemed separate, it gains a special kind of authority. It does not just solve one puzzle, it redraws the map. Maxwell gave physicists a vision of light that was both concrete and expansive. It was a wave in electric and magnetic fields, travelling through space at a definite speed, obeying precise laws, fitting neatly into a unified account of nature. In that intellectual climate, the wave view of light did not feel like one option among many. It felt like the answer. There was, however, one lingering point that many physicists of the time found difficult to let go of. If light was a wave, what exactly was waving? Water waves move in water. Sound waves move in air or some other material. A wave, in ordinary experience, usually needs a medium. Something has to do the actual oscillating. So if light travels through the vacuum of space, crossing the emptiness between the sun and Earth, what is it a wave in? This led to the idea of the luminiferous ether, a hypothetical medium filling all space, subtle enough not to slow planets or clutter the cosmos, yet solid enough in some sense to support the propagation of light waves. The ether was one of those ideas that seems almost inevitable once you commit to the assumptions of the time. It was not invented because scientists were being fanciful. It was invented because waves, as then understood, seemed to require a medium, and light seemed very strongly to be a wave. So something had to carry it. The ether would be everywhere and nowhere noticeable, present throughout the universe, invisible, intangible, but physically necessary. It was an elegant patch, though perhaps a suspiciously convenient one. The history of science is full of these entities that arise because a theory needs them to complete its picture. Sometimes they turn out to be real, sometimes they quietly exit through the back door a few decades later. Even with this unresolved question about the medium, the wave picture remained dominant because it worked so well where it counted. In laboratories and calculations, it kept delivering. And science is often willing to tolerate a bit of conceptual untidiness if the predictive machinery is strong enough. One can almost imagine a physicist of the period saying, "Yes, the ether is a little strange, but look at what the wave theory gets right." And that would have been a fair defense. A theory does not have to answer every imaginable question at once to earn trust. It has to organize the evidence better than its rivals. Another reason the wave picture felt so compelling was that it carried the authority of continuity. Waves are smooth. They spread their influence over space. They vary gradually. That smoothness fits naturally with many older habits of thought in physics, especially the desire to describe change with continuous mathematics. Classical mechanics had already accustomed physicists to differential equations, to systems evolving in elegant continuous ways. The wave theory of light fit that aesthetic beautifully. It suggested a world that was orderly, analysable, and continuous down to its roots. There is something comforting in that image. It presents nature as something whose complexities arise from lawful motion, not sudden little jumps or indivisible packets arriving one by one like impatient knocks at the door. And it is worth remembering that this period was not merely an age of wrong ideas waiting to be corrected. That would be much too smug a way to tell the story. The wave theory was not a mistake in the ordinary sense. It captured something real and important. Light really does show interference and diffraction. It really is described extraordinarily well by electromagnetic wave theory in a great many contexts. If you build an optical instrument, study radio transmission, or calculate how waves propagate in many practical settings, the wave picture is not an embarrassing relic. It is indispensable. This matters because the eventual quantum revolution did not arrive by simply declaring the wave view false. It arrived by showing that the wave view, for all its power, was not complete. That incompleteness was difficult to see at first precisely because the successes were so impressive. When a theory is working beautifully, there is a natural tendency to assume any remaining problems are minor repairs waiting to be made. Perhaps a few loose ends need tying up. Perhaps a more refined understanding of the ether will settle the medium question. Perhaps some unusual experimental results will eventually be folded into the existing structure. Scientists are human beings, after all. They do not lightly abandon a framework that has rewarded them with clarity, prediction, and intellectual elegance. So by the late 19th century, the world of physics had strong reasons to believe waves had won. Light as an electromagnetic wave was one of the great triumphs of classical science. It fit the evidence, unified fields, and carried an explanatory power that was hard to rival. In that sense, waves ruled the world not because physicists were stubborn, but because nature had given them many reasons to think so. The theory deserved its prestige. That is exactly why the cracks that later appeared were so disruptive. If the wave picture had been weak, its replacement would not have felt like a crisis. But it was strong. It had earned trust. And when trouble came, it came not to a flimsy idea, but to one of the crown jewels of classical physics. There is also a deeper lesson in this stage of the story. The power of the wave picture shows how science often progresses. A theory can be profoundly right within a wide domain and still not be the final word. That is not failure, it is growth. The world is large enough that even our best descriptions may turn out to be pieces of a larger structure. Classical wave theory was one such piece. It illuminated a great deal. It still does. What it could not do, as physicists would slowly discover, was account for every way light interacts with matter. And that is where the mood begins to shift. For all its success, the wave view would soon encounter phenomena that did not sit comfortably inside smooth, continuous oscillation. There were situations in which light behaved as though it delivered energy in little separate chunks, rather than in a continuous spread. There were experiments in which the elegant wave story started to stumble, and the older particle language, which had looked rather outdated for a while, began to stir again in the background like a character in a mystery who was dismissed too early and now returns with inconvenient relevance. For the moment, though, it is worth sitting just a little longer with the confidence that waves once inspired, because without that confidence, the next turn in the story does not land with full force. Physics was not wandering in confusion when it embraced waves. It was standing on a strong and beautiful structure that had every appearance of permanence. Light seemed to belong to the great family of continuous disturbances that spread through space, overlap, and interfere. The theory behind that picture was rich, productive, and deeply persuasive, which is precisely why it became so unsettling when nature began to suggest that the hard, little certainty of particles had not been banished after all and might still have something essential to say. For all the elegance and prestige of waves, there was always something deeply persuasive about particles. They carry a kind of hard little certainty that waves do not. A particle seems like the sort of thing the mind can grip. It has a place, it has a path. It starts here, goes there, strikes that, bounces off this. Even if it is too small to see, the picture feels manageable. You can imagine it, you can draw it. You can follow its journey from one moment to the next without feeling that reality has quietly slipped out of the room while you were trying to label it. This is one of the reasons the particle idea never fully disappeared, even in the great age of waves. It was not merely an old opinion hanging on out of habit. It answered to something basic in the way human beings understand the world. We are very used to small objects behaving like miniature versions of larger ones. Sand falls grain by grain. Rain comes in drops. Dust floats in little specks. Shot pellets scatter. Seeds bounce off stone. If a thing is tiny enough, we tend to imagine it as a tiny object, not as a spread-out disturbance. That habit of thought goes very deep. It is not irrational. In many ordinary situations it works extremely well, and before light became the central troublemaker of this story, particles already had a strong foothold in physics because matter itself seemed to invite that picture at every turn. Long before anyone could directly probe atoms in the modern sense, the idea that matter might be made of discrete little constituents had a natural appeal. Break a rock into pebbles, pebbles into grit, grit into dust, and one is tempted to think the process must eventually bottom out in some smallest pieces. There is something satisfying about that. It offers structure. It promises a world built from components. It suggests that beneath the softness and variety of visible things, there might be a durable architecture of little units. That line of thought goes back a very long way. Ancient thinkers speculated that matter might be made of indivisible parts, not because they had decisive evidence, but because the idea possessed a certain logical neatness. If the world is made of changing things, perhaps those changes are arrangements and rearrangements of more basic enduring bits. The details were often far from modern science, of course, but the intuition was powerful. There is a peculiar comfort in imagining reality as a kind of construction set. It allows one to believe that even complexity may have simple ingredients underneath. By the time classical physics matured, the particle way of thinking had become more than a philosophical preference. It had become a practical method. Newtonian mechanics, in particular, gave enormous authority to the image of objects moving under forces along definite paths. This was one of the great successes of science. A planet could be treated as a body with a position and velocity. A cannonball could be described in the same spirit. A falling apple, a swinging pendulum, a tossed stone, all could be analysed by tracking the motion of distinct bodies through space and time. The language of particles fit perfectly into that framework. It made the world feel intelligible in a direct, almost architectural way. This matters because the concept of a particle is not just a claim about smallness, it is a claim about individuality and localization. A particle is this thing rather than that one. It occupies one place rather than many. It can be counted. If there are 5 particles, there are 5, not 5.5 spread vaguely over the table, not one smeared into a cloud of possibility. 5, countable, separable, located. That crispness is intellectually addictive. Once you have a theory that handles the world through distinct entities with definite positions and motions, you begin to trust that style of explanation almost automatically. So when light entered the picture, it was not strange that some scientists wanted to treat it in the same general way. Newton himself famously favoured a corpuscular view, imagining light as made of tiny particles or corpuscles emitted by luminous objects. And it is not hard to see why this seemed plausible. Light travels in what appear to be straight lines. It casts shadows with relatively sharp edges. Mirrors reflect it in a way that can be described geometrically. If you stand in sunlight, the illumination feels directional. One can easily imagine a stream of tiny projectiles flying outward from the source, bouncing off polished surfaces and passing through transparent materials with changes in speed or direction depending on the medium. Indeed, some aspects of optics fit nicely with a particle picture. Reflection is easy to imagine that way. A tiny light corpuscle hits a mirror and rebounds much like a ball from a wall, except with more discipline and rather better manners. Refraction can also be modelled in a particle framework, though the details become more delicate and not always entirely convincing. But the important point is that for a while the corpuscular idea did not look absurd. It looked like a reasonable attempt to extend the successful mechanics of particles into the domain of light. There is another reason particles retain such appeal, and it lies in the way events often arrive in the world. A particle, unlike a wave, tends to announce itself through a hit. It lands, it strikes, it leaves a mark. This is psychologically important. We are very impressed by local events. A bullet hole in a wall, a raindrop on a window, a spark on a detector. These feel like the signatures of little things arriving one by one. Even if one cannot see the object itself, one sees the effect and thinks, yes, something discrete must have done that. A wave may spread its influence broadly, but a particle seems to make a point. That way of thinking became even stronger as the science of matter advanced. Chemistry in the 18th and 19th centuries increasingly supported the idea that substances combine in fixed proportions, as though built from distinct units. Dalton's atomic theory gave this intuition a more formal scientific role. If elements are composed of atoms and compounds arise from combinations of them in definite ratios, then the world begins to look sharply particulate indeed. Later work in statistical mechanics and the kinetic theory of gases reinforced the image. Gas pressure could be understood as the result of countless tiny particles in motion, colliding with the walls of a container. Heat itself could be connected to their motion. Suddenly, particles were not only conceptually tidy, they were extraordinarily productive. The kinetic theory is worth lingering over because it shows just how much explanatory power the particle picture came to possess. Instead of treating a gas as a smooth continuous substance only, scientists could understand its behavior through the invisible motion of innumerable molecules. Pressure, temperature, diffusion, all these could be interpreted through the statistical behavior of particles. It was a triumph of indirect reasoning. No one needed to watch each molecule personally with a notebook and an expression of mild concern. The theory worked because the collective effects matched what one observed. This gave particle thinking a deep legitimacy. The invisible little objects of theory were earning their keep. Even Brownian motion, the jittery motion of tiny suspended grains observed under a microscope, eventually became evidence in favour of molecular reality. The random buffeting of visible particles by invisible molecules helped make the atomic picture feel less like a useful fiction and more like a genuine feature of the world. By the early 20th century, many scientists no longer thought of particles as merely one possible descriptive tool. They thought of them as part of the underlying furniture of nature. Matter, at least, was made of little entities. That seemed increasingly clear. And here we arrive at the hard, little certainty of particles in its full form. A particle is something that gives classical physics what it most loves. It offers definite states. At a given time, a particle has location and emotion, even if we do not know them exactly. Our ignorance is one thing. The particle's actual condition is another. This distinction is crucial. In classical physics, uncertainty is often assumed to be a problem of knowledge rather than reality itself. If you do not know where a grain of dust is, that is unfortunate, but the dust itself is still somewhere. If you do not know exactly where a planet will be in 100 years, it is because the calculation is hard or your data incomplete, not because the planet lacks a path. The world in this picture has sharpness built into it whether or not the observer can fully access it. That classical sharpness feels profoundly sensible. It matches daily life. If you lose your keys, you do not assume they exist as a broad field of possibilities throughout the kitchen. You assume they are in one place, and that you, regrettably, have failed to identify which place. If a train arrives at a station, it occupies a platform, not several platforms in a ghostly statistical haze. The practical world runs on localization. Objects are where they are. This habit of mind, entirely appropriate for large-scale life, became part of the conceptual toolkit physicists carried with them into the microscopic realm. Particles also fit neatly with causality as classical science liked to imagine it. A definite object undergoes definite forces and produces definite outcomes. There is something reassuringly legalistic about the whole setup. This happened because that acted on it. That result followed because this particle struck there. One can tell the story event by event. The world becomes a chain of impacts, trajectories, and interactions. Even when the details are complicated, the style of explanation remains clean. Nothing needs to be spread out more than necessary. Nothing needs to remain indefinite unless our measurements are poor. This is why the return of particle language in the study of light would later carry such force. It was not simply that particles were old-fashioned and therefore quaintly available for reuse. It was that particles represented an entire style of realism that physics found deeply natural. If light could somehow be restored to a particle picture, at least in some contexts, then one regained locality, countability, and definite transfer of energy. One regained the feeling that events happen in clean little packages rather than in continuous washes. There is, however, a subtle tension already present here if one looks carefully. Particle thinking is powerful precisely because it is so sharp, but that sharpness can become a trap when reality refuses to behave in perfectly localized ways. Classical particles do not interfere with themselves. They do not spread through multiple paths and recombine to create bright and dark fringes as waves do. If you fire tiny pellets toward a barrier with two gaps, each pellet goes through one gap or the other. One can then predict a distribution of impacts on the far side based on trajectories and geometry. It may be messy, but it will not display the signature alternating structure of a wave interference. That distinction is not minor, it is fundamental. Still, before confronting that problem directly, it is useful to understand how compelling the particle picture remained in more ordinary contexts. Think again about detection. Even waves, when measured in some instruments, often leave localized marks. This is one of the reasons light's later behavior became so difficult to interpret. A photographic plate, for example, accumulates exposure through countless tiny events. A detector records a click. An atom absorbs energy in a discrete process. Those localized outcomes make one want to say that something little and separate arrived. The particle picture speaks naturally to such observations. It does not ask the mind to imagine a broad continuous field suddenly pretending to be a point. It begins with points, and then there is the matter of energy. In a classical wave, energy is generally distributed across the wave itself. A stronger wave carries more energy, but that energy can be spread over space in a continuous manner. A classical particle, by contrast, carries its own bundle of energy as an individual entity. This difference would become decisive later in the story, when certain experiments showed that light behaves as though its energy is not simply smeared continuously across a wavefront, but delivered in distinct packets. When that moment comes, the old particle instinct will feel vindicated in an extraordinarily dramatic way. It is easy, from a modern vantage, to laugh gently at the confidence of classical certainty, but that would be unfair. Certainty earned through repeated success is not foolish. The particle worldview had earned its authority in mechanics, chemistry, and the growing atomic picture of matter. It organized the world with tremendous efficiency. It let scientists think in terms of objects and interactions, causes and effects, positions and motions. If later developments complicated that clarity, it was not because the older picture had been worthless. It was because it had worked so well that nature had to produce very stubborn evidence indeed before physicists were willing to accept anything stranger. There is also an emotional side to this that is easy to overlook. Particles satisfy the desire for reality to have edges. A wave can feel elusive, it spreads, it blends. It can be in many places at once in an ordinary descriptive sense. A particle, by contrast, reassures us that somewhere underneath the blur there is a this rather than a that. It preserves the notion that the world is composed of entities with identities. In that way, particles are not just a scientific concept. They are almost a philosophical comfort. They promise that if we could only look closely enough, the world would resolve into hard little somethings. That promise is part of why the quantum story becomes so strange later on. Quantum objects will not let us keep all the comfort that particles offer, yet they will not let us abandon particles entirely either. When measured, they often show up with all the localized definiteness one associates with particle behavior. They arrive as a click here, a mark there, a single event at a detector. But between such events, or in the structure of their probabilities, they behave in ways classical particles should not. The trouble is not that particles were obviously wrong. The trouble is that particles were too right in some ways and too limited in others. Before that difficulty fully announces itself, classical physics still allows us to enjoy a relatively orderly picture. Matter is particulate. Motion is definite. Light, even if increasingly treated as a wave, can still in some contexts be imagined as travelling in rays with geometric discipline. One can keep the categories reasonably separate and tell a coherent story. Waves belong to certain phenomena, particles belong to others. The world remains sorted. It is only when certain experiments begin forcing both descriptions into the same corner that the clean division starts to collapse. And perhaps that is the key thing to carry forward from this stage of the story. Particles were not merely one half of an abstract contrast. They represented a whole way of doing physics, a whole expectation about what explanation should look like. They offered locality, individuality, discreteness, and the promise that uncertainty was only ever temporary ignorance. That is the hard little certainty of particles. It is hard because it gives the impression of something solid and final. It is little because it imagines the world built from tiny self-contained units. And it is certainty because it insists that reality, beneath our incomplete knowledge, always has definite answers ready and waiting. The difficulty, as we are about to see, is that nature seems perfectly capable of using the language of particles when it suits her, then turning around and producing patterns that make no sense unless something wave-like has also entered the room. And nowhere does that become more unsettling, more elegant, or more impossible to ignore than in the experiment with two slits and far too many answers. There are few experiments in all of physics that have caused as much trouble with as little equipment as the double-slit experiment. It is not grand in the way a giant telescope is grand. It does not require a mountain, a particle accelerator stretching for miles, or a machine that hums like it is plotting against the electric bill. At its heart, it is almost offensively simple. You have a source that sends something toward a barrier. The barrier has two narrow openings in it. Beyond the barrier sits a screen that records where the incoming stuff arrives. That is all. It sounds like the sort of thing one might set up in an afternoon, feel quite pleased with, and then go home expecting a quiet evening. Instead, it became one of the most famous sources of confusion in modern science. The reason it matters so much is that it asks reality a very basic question in a very clean way. If something has two possible paths through two slits, what pattern does it make on the screen behind them? In classical physics, the answer depends on what kind of thing you are sending in. If you are sending particles, little localized objects like grains or pellets, then each one goes through one slit or the other and lands somewhere on the screen. Over time, you get two broad clusters of impacts lined up with the slits. There may be some spread because not every particle travels in exactly the same way, but the basic result is clear. Two openings give two piles, sensible, manageable, nothing dramatic. If on the other hand you are sending waves, the expectation changes. A wave approaching the barrier passes through both slits, in the sense that the disturbance spreads through both openings. On the far side, the waves from the two slits overlap. In some places the crests line up and reinforce each other. In other places a crest from one side meets a trough from the other, and they reduce or cancel. The result is not simply two bright regions behind the slits. It is an interference pattern, a series of alternating bands, strong in some places, weak or absent in others. That is the classic signature of wave behavior. So the experiment seems, at first glance, like an excellent sorting machine. If you are not sure whether something is a wave or a particle, send it through two slits and see what happens. This is exactly why the experiment became so important in the study of light. When light was sent through two slits, the result was an interference pattern. Bright and dark bands appeared on the screen, not just two simple lit areas. That strongly suggested light was acting like a wave. It was one of the most convincing pieces of evidence in favour of the wave picture. If you had stopped the story there, you might have felt quite comfortable. The experiment had done its job. Light belonged with waves, case closed. But physics is very fond of reopening cases just when the paperwork looks complete. The trouble deepened when physicists began asking the same question not only of light, but of matter, especially electrons. Electrons had strong credentials as particles. They carried charge. They could be deflected by electric and magnetic fields in ways that made them seem like tiny, localized bits of matter. They could strike detectors in individual events. If anything in the microscopic world deserved to wear the particle badge with confidence, it was the electron. And yet, when electrons were sent through a double-slit arrangement under suitable conditions, the screen again showed an interference pattern. Not two broad particle piles, an interference pattern. That was bad news for common sense and excellent news for future generations of bewildered students. One might try to avoid the problem at first by saying that perhaps the electrons were being sent in a dense stream and somehow jostling one another, creating a collective wave effect. That sounds comforting for about 5 minutes. So physicists did the sensible thing and reduced the intensity. They sent electrons through one at a time, with enough separation that each electron passed through the apparatus long before the next one arrived. If classical particles were what they seemed to be, then each electron should pass through one slit or the other, and simply add one dot to the screen. Over time, the dots should accumulate into two broad regions, but that is not what happened. The dots arrived one by one, each in a definite place, exactly as particles seem to do. Yet after many such individual arrivals, the overall pattern that emerged was still the interference pattern. Each electron behaved as though it contributed to a wave-style distribution, even though it arrived as a localized hit. This is where the experiment stops being merely interesting and starts becoming deeply uncomfortable. If electrons are particles, how does a single one contribute to an interference pattern? Interference requires overlapping possibilities from the two paths. It looks as though the electron in some sense behaves like a wave while travelling through the setup, then like a particle when it is detected. But saying that too quickly can be misleading, because it sounds as though the electron neatly changes costume halfway through the experiment, which is not quite what the theory says. What the experiment really reveals is that the old categories are no longer sufficient on their own. The natural question then becomes one that seems simple, but turns out to be dangerous. Through which slit did the electron go? That sounds like the sort of thing any respectable object should be able to answer. Left or right, one or the other. But when physicists tried to determine which slit the electron actually passed through, something remarkable happened. The interference pattern disappeared. Once the setup included a way of finding out which path was taken, the screen no longer showed the familiar bands. Instead, it showed the sort of distribution one would expect from particles going through one slit or the other. In other words, when path information became available, the wave-style interference vanished. This is one of the most important facts in all of quantum mechanics, and also one of the easiest to say in a way that creates confusion. It is tempting to put it in mystical language and claim that the electron somehow knows it is being watched and changes its behaviour out of shyness or theatrical pride. That is not the right way to think about it. The issue is not human awareness in the ordinary sense. The issue is measurement, physical interaction, the experimental arrangement itself. To determine which slit the electron goes through, the apparatus must interact with the electron in a way that distinguishes the paths. Once that happens, the conditions needed for interference are destroyed. The wave-style combination of possibilities no longer survives intact. Still, even when stated carefully, the result is unsettling. Without path detection, the electron produces an interference pattern as though both paths matter. With path detection, the interference disappears and the results look particle-like. The experiment does not simply reveal what the electron was doing all along. The kind of question you arrange the apparatus to answer affects the kind of behaviour that can appear. That is why the double-slit experiment does not merely give one answer, it gives too many. Ask whether the system produces interference, and it says yes. Ask which path was taken, and it gives you an answer compatible with that question instead. But the two styles of answer do not fit neatly into one classical picture. This creates a problem at the level of ordinary storytelling. Classical physics likes a narrative in which things have properties, move through space, and produce outcomes. In that kind of story, the experiment reveals what happened. The particle went through the left slit and landed here, or it went through the right slit and landed there. The screen records the result, but the path was always definite. The double-slit experiment resists that story. If you insist that the electron must have gone through only one slit even when no path measurement is made, then it becomes very hard to explain the interference pattern. Classical particles that take one path do not interfere in this way. If you instead say the electron was simply a wave spread through both slits, then you must still explain why the detector always records a single, localized arrival. A wave spread out across the screen does not ordinarily produce one neat click at one point. That combination is the heart of the matter. The motion through the apparatus seems to require a wave-like description. The detection on the screen seems to produce a particle-like event. The experiment therefore acts like a machine for exposing the limits of our categories. It does not let waves rule completely, because the final outcomes are discrete. It does not let particles rule completely, because the distribution of many outcomes carries the structure of interference, And then, just to make life harder, it changes the result when you ask for which path information. At this point, people often ask whether the electron literally goes through both slits at once. That phrase is understandable, but it needs careful handling. In ordinary language, it suggests a tiny object physically splitting like a drop of water and later rejoining itself, which is not quite right. The quantum description does not say the electron is a little billiard ball cut into pieces. It says that the state associated with the electron evolves in a way that includes contributions from both possible paths. Those contributions can combine and interfere. The thing that behaves like a wave in this context is not a little material smear in the old classical sense. It is the quantum state, the mathematical object used to assign probabilities to different outcomes. That distinction matters because it helps avoid one of the common misunderstandings about the double-slit experiment. The wave involved is not simply a hidden blob of substance sloshing through space like water. It is a more abstract, more constrained kind of wave. It tells you about the range of possible outcomes and how those possibilities combine. Where the wave description predicts strong reinforcement, detections are more likely. Where it predicts cancellation, detections are unlikely or absent. Over many trials, the pattern of individual hits reflects that probability structure, but each single event remains definite. One electron is detected at one place, then another is detected elsewhere. The interference pattern emerges statistically, not as a continuous glowing wave spreading permanently across the screen. That is one reason this experiment is so effective at unsettling people. It attacks both of our preferred intuitions at once. We like particles because they give definite events. The experiment preserves that at the detector. We like waves because they explain interference. The experiment preserves that in the distribution. But it does not let us merge those comforts into one classical picture. Instead, it gives us a hybrid demand. Use the wave-style description to calculate probabilities, expect particle-style outcomes when a measurement is made, and do not assume that behind these descriptions there must exist a hidden classical account that keeps all the old categories intact. Of course, many people have tried to recover such an account. Some interpretations of quantum mechanics seek a deeper underlying reality, in which the quantum state and the observed outcomes are connected by hidden variables or alternate structures. Others argue that the formalism itself is the correct guide and that demanding an ordinary visual picture is asking for something the theory does not owe us. These debates are important, but they should not distract from the experimental fact itself. No matter how one interprets the theory, the double-slit experiment forces one to accept that wave interference and localized detection are both part of the behavior being described. The experiment does not wait politely for philosophers to agree before continuing to produce the same awkward result. There is also a special cruelty in how simple the apparatus looks. If the experiment were wildly complicated, full of specialized machinery and exotic materials, one might comfort oneself by saying the oddness is probably buried in technical details, but the double-slit setup is almost embarrassingly direct. Source, barrier, slits, screen. The strangeness is not hidden in a thicket of engineering. It stands in plain view. That is part of why so many physicists have used this experiment as a touchstone. It strips the problem to its essentials. It asks just enough of reality to expose something fundamental. Richard Feynman famously treated the double-slit experiment as containing the central mystery of quantum mechanics, and one can see why. It is not that every detail of the whole theory is present in one small setup. Rather, the experiment captures the essential conflict between classical categories and quantum behavior. It reveals superposition in the sense that multiple alternatives contribute to the evolution of the state. It reveals interference between those alternatives. It reveals the role of measurement in selecting definite outcomes. And it reveals the difficulty of assigning a simple path story when no measurement establishes such a path. All of that, from two narrow openings in a barrier. It is really rather rude of the experiment when you think about it. Another way to appreciate the problem is to compare what happens when one slit is open versus when both are open. With one slit open, you get a certain distribution on the screen, broad but understandable. Open the other slit by itself, and you get a similar distribution shifted to match the different path. Classical thinking suggests that opening both slits should simply give the sum of the two one-slit results. More ways through should just mean more arrivals added together, but with quantum particles like electrons and with light under the right conditions, that is not what you get. Opening both slits changes the pattern in a way that is not just additive. Some regions that would have received particles from each slit individually become unexpectedly dim or empty when both are open. Some regions become more intense. This is the unmistakable mark of interference. The alternatives do not merely coexist. They combine in a way that changes the probabilities themselves. That last point is one of the clearest signals that the old language is too small. In classical probability, if an object can take one route or another, and the routes are independent alternatives, the total probability is the sum of the probabilities for each route. In quantum mechanics, the combination happens at a deeper level before probabilities are finally extracted. That is why the pattern from two slits is not just the arithmetic addition of one-slit patterns. The possibilities interfere before the definite outcome is recorded. The old logic of either this path or that path is not enough on its own. Yet we should be careful not to exaggerate this into nonsense. The double-slit experiment does not mean reality is arbitrary, or that logic has collapsed into a heap on the floor. The quantum rules are precise. They tell you how to calculate the distribution. They tell you when interference should appear and when it should disappear. What changes is not the existence of lawful behaviour, but the kind of lawful behaviour nature exhibits. The classical expectation that objects always have definite hidden paths waiting to be uncovered is what comes under pressure. The experiment suggests that path-definite language may not apply in the same way when no measurement establishes such a path. This is why the experiment produces too many answers. It does not answer the old question with a single familiar identity. It says if you set up the apparatus to preserve interference, the result reflects the combination of multiple possibilities. If you set it up to reveal a path, the interference is lost and the outcome reflects distinguishable alternatives. If you insist on asking what the electron really was doing in classical terms all along, the experiment becomes uncooperative. It will give you results, but not the simple hidden story you were hoping for. There is something almost educationally cruel in the way this works, because the experiment tempts you to oversimplify and then punishes you for it. Call the electron a particle, and the interference pattern objects. Call it a wave and the localized detections object. Say it is both in the ordinary classical sense and the measurement story becomes slippery. Say the apparatus just reveals what was already true, and the dependence on which path information causes trouble. Each easy answer works for a moment and then collapses under the weight of the next fact. The experiment is like a patient instructor who allows every naive interpretation just long enough for it to fail on its own. And still, for all its reputation, the double-slit experiment is not a trick. It is not a paradox manufactured by clever wording. It is a real and repeatable piece of physics. Light does this, electrons do this. Other quantum systems can be made to do versions of it as well. The problem is not that the data are unclear. The problem is that the data are too clear and our old categories are too narrow. That is a much more serious kind of problem. So when people say the double-slit experiment shows that quantum objects are both waves and particles, it is worth hearing that as a rough first step rather than a final account. It points in the right direction because it acknowledges both sides of the behaviour. But the deeper lesson is that the quantum description is not simply the classical wave picture glued to the classical particle picture with a bit of optimistic tape. Something more basic is going on. The experiment reveals that what evolves through the apparatus behaves in a way that must be treated with wave-like mathematics, while what is finally recorded in measurement appears as a definite event. The gap between those two is not a minor inconvenience. It is the place where quantum theory begins to speak in its own voice, and once that voice has been heard, the next difficulty arrives almost immediately, because if the double-slit experiment made light look deeply wave-like, there was another line of evidence waiting in which light behaved, with a stubborn discreteness that waves alone could not comfortably explain. That was the moment when light started acting less like ripples and more like a shower of tiny separate impacts, and the whole balance of the story shifted again. By the end of the 19th century, light had done quite a convincing job of presenting itself as a wave. It interfered, it diffracted, it could be polarized. Maxwell had wrapped it inside a grand electromagnetic theory that was powerful enough to make physicists feel they were not just describing light, but finally understanding what it was. If you had asked a well-informed scientist of that era what light really amounted to, there is a good chance the answer would have come back with a fair amount of confidence. Light was an electromagnetic wave. There might still be technical questions to sort out, of course. Science always has technical questions to sort out. But the broad picture looked stable, and then light began to misbehave in a way that waves were not supposed to. The trouble came from a set of experiments involving metal surfaces and shining light on them. At first glance, this does not sound like the sort of arrangement that should overturn anyone's worldview. A metal plate, a source of light, a few measurements, hardly the stuff of cosmic drama. But physics often reserves its biggest disruptions for the simplest setups. You ask a modest question, and the universe replies in a way that ruins several decades of confidence. The basic observation was this: under the right conditions, light shining on a metal can caused the metal to emit electrons. These emitted electrons came to be called photoelectrons because they were released by light. That alone was already interesting, but not necessarily shocking. One could imagine light as a wave, carrying energy to the electrons in the metal and eventually giving them enough of a push to escape. There was nothing obviously impossible about that in classical terms. A wave can transfer energy. Stronger light should mean more energy available. If electrons are bound inside the metal, perhaps enough incoming wave energy can shake them loose. Fair enough. But when physicists looked more closely, the results did not line up with that simple wave story. The first problem was the role of frequency. In the wave description of light, intensity is usually associated with how much energy the wave is carrying overall. So one might reasonably expect that if you increase the intensity of the light, you should be able to knock electrons out of the metal more effectively, regardless of the colour or frequency, provided the light is strong enough. A very intense red light, for example, ought eventually to do the job if it dumps enough energy into the metal. That is what classical wave thinking would naturally suggest. Instead, what the experiments showed was that below a certain frequency, no electrons were emitted at all, no matter how intense the light was. You could shine a bright enough low-frequency light on the metal for as long as you liked, and still nothing happened. The electrons stayed put with admirable stubbornness, but once the light frequency rose above a certain threshold, electrons were emitted, and they came out promptly. That was strange. It suggested that the colour of the light mattered in a more fundamental way than the total wave intensity alone. The second problem was the speed of the response. In a classical wave picture, if energy is spread continuously across the light wave, then one might expect an electron in the metal to need time to soak up enough of that distributed energy before escaping. Especially if the light is weak, there ought to be some measurable delay while the energy accumulates. Think of it as trying to fill a bucket from a slow tap. If the water is coming in gently, it takes time before the bucket reaches the brim. But that is not what happened. When the frequency was high enough, the emission of electrons occurred essentially without delay. Even very weak light above the threshold frequency could knock electrons out immediately. There was no obvious waiting period during which the electron patiently gathered little sips of wave energy until it had enough to break free. It was more as though each electron either got what it needed in one go or did not get it at all. The third problem involved the energy of the emitted electrons themselves. Classical wave reasoning would lead you to think that if you make the light more intense, the emitted electrons should come out with more energy, since more incoming wave energy should mean a stronger push. But what the experiments revealed was that the maximum energy of the emitted electrons depended mainly on the frequency of the light, not its intensity. Increasing the intensity increased the number of emitted electrons, provided the threshold frequency was already met, but it did not increase their maximum individual energy in the expected way. That is a very odd result, if you're thinking in terms of a smooth wave bathing the metal surface. Taken together, these findings were deeply awkward for the classical wave theory of light. They did not merely require a small adjustment around the edges, they pointed toward a more radical conclusion. Light seemed to be interacting with matter as though its energy came in discrete packets, not an endlessly divisible spread, not a smooth drizzle over the whole surface. Packets, little bundles delivered in separate hits. This was the moment when the old particle instinct began to stir with renewed seriousness. It was one thing for light to show interference in the double-slit experiment and look wave-like. It was another thing entirely for it to strike matter as though arriving in tiny separate bursts, each one capable of transferring a definite amount of energy to a single electron. That behaviour looked much less like a ripple, and much more like a shower of bullets. Now, that comparison can be useful as long as we do not take it too literally. Light is not made of miniature metal pellets, and the quantum description that eventually emerged is subtler than a simple return to Newton's old corpuscles. Still, from the point of view of experimental feeling, the resemblance was undeniable. The interaction looked local and discrete. One bit of light seemed to give one electron a definite kick. If the kick was strong enough, the electron escaped. If not, it did not. There was a certain hard-edged economy to the whole thing. No pooling of smooth wave energy over time, no gradual build-up, just individual exchanges. The scientist most closely associated with making sense of this was Albert Einstein. That is one of those facts that can be slightly overshadowed by his later fame, because when people hear his name they tend to think first of relativity, clocks, gravity and hair that looked as though it had been struck by several independent theories at once. But in 1905, the same astonishing year in which he published work on special relativity, Einstein also proposed a bold explanation for the photoelectric effect. He suggested that light itself could be treated, in certain interactions, as though it were made of discrete energy quanta. This was not merely a clever patch, it was a serious conceptual risk. By that time, the wave theory of light was so successful that suggesting a particle-like aspect for light felt almost backward. It threatened to reopen a question many thought had already been settled, but Einstein's proposal had a decisive virtue. It explained the facts. In his picture, light of a given frequency comes in packets, each packet carrying an amount of energy determined by that frequency. An electron in the metal does not slowly absorb little scraps of energy from a broad incoming wave. It interacts with one packet of light. If that packet has enough energy to overcome the binding of the electron in the metal, the electron is emitted. If it does not, the electron remains trapped. This immediately explains why there is a threshold frequency. Below that frequency, each packet is individually too weak, no matter how many packets arrive overall. Increasing the intensity merely sends more low-energy packets, not stronger ones. If none of them individually have enough energy, then none can free an electron. It also explains the absence of delay. The electron does not need to wait for energy to accumulate gradually from a smooth wave. It gets the energy in a single interaction. Either that interaction is sufficient or it is not. No bucket filling required, and it explains why increasing intensity above the threshold frequency increases the number of emitted electrons rather than the maximum energy of each one. More intensity means more packets arriving, which means more opportunities for electrons to be knocked loose, but the energy of each individual packet still depends on frequency, so the maximum energy of each emitted electron is set by that, not by the total brightness alone. This was an extraordinary moment in the history of physics, because it did not simply add one more odd feature to light. It forced a change in what light could be said to be. For decades the wave story had ruled with great authority. Now here was a phenomenon that seemed to require light to behave in a way waves alone could not explain. It was not enough to say that light was mostly a wave, but occasionally a bit inconvenient. The evidence was too clean for that kind of polite dismissal. Of course, not everyone accepted Einstein's idea immediately. That is quite understandable. The wave theory of light had earned its place. One does not throw over a successful framework lightly. And Einstein's proposal, at first, sounded almost like a step backward to a cruder age, except that it explained the new data much better than the old theory did. Science can be conservative in the healthier sense. It does not abandon a strong model because someone produces a bold thought. It wants evidence, predictions, and consistency. Over time, more evidence accumulated and the case grew stronger. There is an important subtlety here that is worth pausing over. Einstein was not saying that everything the wave theory had explained was suddenly wrong. Light still diffracted. It still interfered. Maxwell's theory was not tossed into the bin like an old receipt. Rather, the lesson was that the wave picture, though powerful, did not tell the whole story about how light interacts with matter. In some contexts, light had to be treated as if it came in discrete quanta. Later, these quanta would come to be called photons. That name helps because it gives the concept a proper noun and allows textbooks to proceed with an air of calm authority, but the calm can be misleading. The underlying situation is still strange. The photon is not simply a classical particle in miniature. It is the quantum object associated with light, and it inherits the same refusal to fit neatly into the old categories. What made the photoelectric effect so important was not merely that it added a particle-flavoured detail to the story of light. It did something deeper. It made it impossible to keep wave and particle comfortably separated by assigning one to light and the other to matter. That older arrangement had at least been tidy. Light could be a wave. Matter could be made of particles. Everyone would stay in their designated seats. But once light itself started acting in discrete particle-like exchanges, that neat division collapsed. The categories had been breached, and there was something psychologically significant about the particular way in which they were breached. The double-slit experiment had already shown light acting in a spread-out interference pattern which felt very wave-like. The photoelectric effect now showed light behaving in a local, one-by-one, all-or-nothing manner when interacting with electrons. That local discreteness is exactly the kind of thing particles are good at. So light now appeared to possess both forms of evidence. It was not merely that scientists were confused about which label to choose. It was that each label seemed justified by different experiments, and neither could simply erase the other. If you imagine the scientific community at this point, you can feel the discomfort. Classical physics had depended heavily on clear categories. A thing was either one sort or another. If a phenomenon behaved wave-like, you used wave theory. If it behaved particle-like, you used particle mechanics. But light was now refusing to stay put. It was as though a witness in a trial had provided an airtight alibi, and then, quite cheerfully, confessed anyway. There is also a broader lesson hidden in the photoelectric effect, one that becomes more obvious in hindsight. The experiment showed that what matters is not only how light travels, but how it exchanges energy with matter. Classical wave theory described propagation beautifully, but when it came to the microscopic bookkeeping of interaction, it ran into trouble. Quantum theory would eventually succeed in part because it took that bookkeeping seriously. It treated interactions not as endlessly divisible flows, but as structured in discrete ways. This discreteness had already been hinted at elsewhere in physics. Max Planck, in his work on black-body radiation, had introduced the idea that energy exchange in oscillators might come in quantized amounts. At first, Planck himself treated this more as a mathematical device than a declaration about the deep nature of reality. Einstein went further by taking the quantum idea seriously for light itself. That step was bolder, and it carried the strange implication that the electromagnetic wave picture was somehow incomplete at the very point where energy is delivered. One can see why this felt so disruptive. Science had spent centuries trying to reduce mystery, by sorting the world into well-behaved kinds. Waves had their properties, particles had theirs. The hope was that once you knew which kind of thing you were dealing with, the right theory would follow. The photoelectric effect challenged that style of confidence. It suggested that the world at small scales is not built to honour those categories in a simple way. What mattered was not attaching a permanent identity card that said wave or particle, but understanding the rules governing different kinds of experimental situations. At this stage of the story, though, it would have been easy to overreact and say that the wave theory of light had been defeated outright. That would have been the wrong lesson. Light did not stop interfering because the photoelectric effect had arrived. Diffraction did not disappear in embarrassment. The wave description remained indispensable. What changed was the realization that the wave description could not be the full story. Light could not be understood as merely a classical wave any more than it could be reduced to merely a classical particle. The old argument had not been resolved in favour of one side. It had been transformed, and that transformation matters because it begins to reveal the shape of the quantum answer. The quantum view does not say that light is secretly one thing, and science has simply not made up its mind yet. It says that the classical concepts of wave and particle are limited tools, each capturing part of the behaviour in particular contexts. In propagation and interference, the wave language is powerful. In localized interactions and energy exchange, particle language becomes essential. The quantum object does not belong comfortably to either classical category, even though it can exhibit features that strongly resemble both. The day light behaved like bullets was therefore not a day when science finally corrected a small mistake. It was a day when reality refused to let one successful picture become universal. The neat wave triumph of the 19th century was interrupted by a fact too stubborn to ignore. Light could strike matter in discrete packets. It could produce immediate local countable outcomes. It could act as though its energy came not in a smooth wash, but in separate little blows. That discovery did not solve the puzzle of light. It made the puzzle sharper. For now, light had two dossiers. One was full of interference, diffraction, and all the graceful evidence of waves. The other was full of quanta, thresholds, and abrupt one-by-one exchanges that looked unmistakably particle-like. To keep both dossiers on the table at once required a new kind of theory, one that did not merely choose sides but change the question. And once that change began, it did not stop with light. Because if light, the old champion of wave behaviour, could also act in these discrete particle-like ways, then the next shock was almost cruelly symmetrical. Matter, which seemed so firmly particulate, would begin to show interference of its own. Electrons would start behaving in ways that made them look less like tiny hard pellets, and more like something that could spread, overlap and interfere. The categories were not just fraying at the edges now, they were being pulled apart from both directions at once. If light behaving like little packets was awkward, electrons returning the favour by behaving like waves was something else entirely. It is one thing for the old wave champion to surprise everyone by acting discreet. That is troubling, yes, but perhaps one can still tell oneself that light was always a bit unusual. Light has a history of making physicists work harder than they had planned. Perhaps it belongs in some special category of its own. Perhaps it is the exception. Perhaps one can keep matter safely on the particle side and preserve at least half the old order, and then electrons arrive and ruin that comforting arrangement. Electrons, after all, seem like exactly the sort of things that ought to be particles. They carry electric charge, they can be accelerated, they can be deflected by electric and magnetic fields, they can strike a detector and produce a single localized mark. They belong to atoms, they move through wires. In laboratory instruments, they behave in ways that make it very natural to imagine them as tiny compact bits of matter. Not visible, of course, but still little objects with positions and motions. If any entity seemed entitled to the hard little certainty of particlehood, it was the electron. That confidence did not come from laziness, it came from success. By the early 20th century, electrons had become part of serious physics. J.J. Thomson had identified the electron through experiments with cathode rays, showing that something with a definite ratio of charge to mass was involved. Robert Millikan had measured the elementary electric charge in a way that gave the electron even more concrete standing in the scientific imagination. The electron was not just a speculative convenience, it was part of the growing furniture of reality. Small, yes. Invisible to the eye, yes. But still the sort of thing people increasingly felt they understood as an individual constituent of matter. So when the question arose whether matter itself might have some wave-like aspect, it sounded almost unreasonable. Not impossible perhaps, because physics by that point had already learned not to overuse that word, but unreasonable in the sense that it strained the categories people still relied on. Waves belong to light, to sound, to water, to fields. Particles belong to matter. The photoelectric effect had already unsettled the first half of that division. To disturb the second half as well felt positively impolite. The idea that matter might have a wave aspect is often associated with Louis de Broglie, and rightly so. In the 1920s, he proposed something bold and deeply suggestive. If light, long treated as a wave, could under some conditions behave as though it came in particle-like quanta, then perhaps matter, long treated as particulate, might under some conditions show wave-like behaviour. There is a kind of symmetry in that thought that makes it feel almost obvious in hindsight. At the time, though, it was a substantial leap. It was not merely saying that the world is complicated. It was proposing that the division between wave and particle might be much less fundamental than classical physics had assumed. One of the reasons de Broglie's idea mattered so much is that it was not just philosophical. It pointed toward measurable consequences. If electrons have a wave aspect, then under the right circumstances they should exhibit interference and diffraction, the same sorts of wave behaviours that had been so important in the case of light, and that in turn meant the idea could be tested. Science is always at its most interesting when a bold idea risks embarrassment in the laboratory. The evidence came, and when it did, it was not kind to common sense. Experiments showed that beams of electrons could produce diffraction patterns when scattered from crystalline materials. This is crucial because diffraction is not the sort of thing classical particles ordinarily do on their own. A crystal, with its orderly repeating structure, can act as a kind of grating for waves. If the incoming thing has the right wave-like properties, the scattered result forms a pattern with definite peaks and valleys, just as one would expect from interference among contributions associated with the regular arrangement of atoms. That is exactly what was observed in the Dalvison and Germer experiment, among others. Electrons fired at a nickel crystal did not merely bounce off in the dull, straightforward manner one might expect from a spray of tiny pellets. They produced angular patterns characteristic of wave diffraction. This was not a minor oddity. It was a direct challenge to the old picture. The electron, that apparently respectable little particle, was showing behaviour that looked deeply wave-like when it propagated through the right kind of setup. It was not a matter of metaphor. It was not a poetic statement about mystery. It was measurable, repeatable, and mathematically structured. The same entity that could strike a detector as a localized event could also spread through possibilities in a way that produced interference patterns. You can probably feel by now why the phrase wave-particle duality became so popular. It is not elegant, but it at least acknowledges the two faces of the evidence. The difficulty is that the phrase can make it sound as though there are two finished classical identities somehow sharing one body, with the electron taking turns between them like an actor changing costumes backstage. That image is understandable, but it is too simple. The real trouble lies deeper, because what is failing is not just our ability to choose the right label. What is failing is the assumption that the old labels refer to complete kinds of thing in the first place. Still, before we move too quickly into the deeper lesson, it is worth dwelling on how stubborn common sense remains at this stage. When people hear that electrons interfere like waves, the first impulse is often to ask what they are really doing in physical terms, Are they spreading out like tiny clouds? Are they somehow splitting into pieces? Are they wiggling through space in a hidden medium? Are they secret particles guided by a pilot wave? Do they pass through both routes at once? These questions are not foolish. They arise because common sense wants a picture. It wants a story involving objects and paths and locations. It wants to know what is happening between the source and the detector. And that is exactly where quantum theory becomes slippery. In classical physics, a path is the sort of thing an object simply has. Even if you do not know it, the object has one. A thrown stone follows a trajectory. A planet follows an orbit. A bead rolling down a track has a sequence of positions. The world may be complicated, but it is narratable. There is comfort in that. One event leads to another. A thing goes from here to there. We may not witness every instant, but we assume the intermediate story exists in a definite way. With electrons in interference experiments, that confidence begins to wobble. Send an electron through a setup with multiple possible paths and do not measure which path it took, and the resulting pattern suggests that the alternatives combine in a genuinely wave-like manner. Try to uncover which path was actually taken, and the interference pattern disappears. The behaviour depends on the measurement arrangement. This does not mean that reality is made of theatrical gestures performed for human observers. It means that the old assumption of a path existing in the same classical sense, regardless of the experimental question, becomes hard to maintain. The best way to appreciate how serious this is may be to think again about the one electron at a time version of interference. It still has the power to unsettle people because it refuses every easy compromise. If many electrons are sent all at once, one might try to imagine that they jostle one another like tiny crowds and somehow produce a collective pattern, but send them through one by one with enough separation that no two are in the apparatus together in any ordinary sense, and the interference pattern still gradually emerges after many runs. Each electron lands in one place, one little hit, one little dot. Yet the statistics of many such dots reveal the familiar bands of constructive and destructive interference. It is as though each electron carries within its behaviour the structure of multiple possibilities, even though the final recorded result is always singular. Common sense does not enjoy this. It would prefer a cleaner choice. Either the electron is a wave, in which case why does it arrive at one place on the screen, or it is a particle, in which case why does the overall pattern show interference? There is an old habit of mind that says contradictory-looking evidence must come from incomplete information, not from a failure of the categories themselves. We want to believe that if only we were clever enough or had better instruments, we would discover the hidden classical story underneath. That instinct is understandable. It is also not something the standard quantum framework rewards in a straightforward way. Part of the trouble is that everyday life trains us very badly for quantum thinking. Our brains evolved to handle medium-sized objects in moderate environments. We're excellent at catching, throwing, stacking, and avoiding things. We're reasonably good at navigating around furniture in the dark, though perhaps less good than we like to think. We're not naturally equipped to understand systems in which possibilities interfere. Measurements alter what can meaningfully be said, and outcomes are governed by probability distributions that are not just summaries of ignorance, but seem woven into the theory itself. That last point is especially important. Classical probability often reflects incomplete knowledge. If you shuffle a deck of cards and I do not know the order, probability helps describe my ignorance. But the deck itself has a definite arrangement. In quantum physics, the probability wave associated with an electron is not merely a bookkeeping device for what we happen not to know about a hidden classical situation, at least not in the standard way the theory is used. The wave structure plays an active role in predicting interference. It is not an optional extra. It tells you where the electron is likely or unlikely to be detected if you repeat the experiment many times. That is a very different kind of role than simple ignorance plays in ordinary life. This is one reason common sense keeps tripping over the question of what an electron is doing when nobody checks on it. The question itself may smuggle in a classical expectation that does not fit. It assumes that a full particle-like description of intermediate behaviour must exist, and that the task of physics is merely to reveal it. Quantum theory, in its standard form, is more cautious. It tells you how the state evolves and how to calculate probabilities for outcomes. It does not always offer a tidy classical narrative about definite hidden paths between measurements. This restraint can feel unsatisfying, but it is not laziness. It is built into the success of the theory. There is also a temptation to say that the electron is somehow indecisive, as though it cannot quite choose whether to be a wave or a particle. That phrasing is charmingly human and completely misleading. The electron is not confused. We are. The problem is not that the electron keeps changing its mind. The problem is that our language was shaped around objects and processes in the ordinary world, and quantum behaviour outruns those habits. The electron is doing whatever electrons do according to the laws of quantum mechanics. It is we who keep trying to force that behaviour into older categories that only partially apply. Another source of confusion comes from visual imagination. We like to picture things. A wave is picturable, so is a particle. But the quantum state associated with an electron is not picturable in the same direct everyday way. We can represent it mathematically. We can visualize probability distributions or wave patterns in simplified forms, but those images are not the same as saying what the electron literally looks like as an object in space at every moment. This gap between mathematics and imagery is uncomfortable, because imagery is one of the tools common sense relies on most. When the picture falters, people often assume the theory must be somehow incomplete or absurd. Sometimes it may indeed be incomplete in the ultimate philosophical sense, but absurdity is too quick a verdict. Mathematics can track structures that common visual intuition cannot. The experimental evidence for electron interference piled up in ways that became impossible to dismiss. Electron diffraction was not an isolated laboratory quirk. It became foundational to our understanding of matter at small scales. The wave aspect of electrons helps explain the structure of atoms, the arrangement of electrons in allowed states, and many features of chemistry and solid matter. Once one accepts that electrons cannot simply be treated as little marbles orbiting a nucleus in the classical sense, many aspects of atomic stability make more sense. The old planetary image of the atom, charming as it was, could not survive. A quantum description was needed, one in which the electron's behaviour is linked to allowed wave patterns and probabilities, rather than neat miniature orbits. This is a good place to notice something subtle. Common sense often objects to quantum theory because it sounds strange, but the alternative is frequently worse. If one insists on keeping electrons as ordinary little particles with ordinary classical motions inside atoms, the consequences quickly become untenable. They would radiate energy in ways that classical theory predicts, and matter would not remain stable in the way it obviously does. The quantum picture may challenge intuition, but it does real explanatory work. It is not merely strange for the sake of drama. It succeeds where the older picture fails, and yet the resistance persists, because common sense has another ally besides everyday experience. Language itself tends to present the world as built from nouns with properties. The electron is this, the wave is that, the particle has a location, the object follows a path. We are constantly pushed towards sentence forms that assume stable kinds. Quantum theory keeps interrupting this by making context matter. The behaviour that shows up depends on how the system is prepared and measured. That does not mean reality is made of words. It means our words were trained on too narrow a slice of reality. Think of how often people ask whether the electron is really a wave or really a particle, as though the word really will force the issue at last. But the more accurate response may be that neither classical word reaches all the way down. Each captures a family resemblance seen in certain circumstances. The wave aspect is evident in interference, diffraction, and the spread of probabilities. The particle aspect is evident in localized detections and discrete interactions. The quantum object is not a compromise halfway between them, nor a simple mixture of both in the old sense. It is something for which those classical concepts are approximations from different angles. That can sound annoyingly abstract, so it helps to return to the experiments. Electrons can produce interference patterns. That is a fact. Electrons are detected as localized hits. That is also a fact. If your conceptual scheme cannot comfortably hold both facts at once, the problem lies with the scheme, not with the laboratory. This is why the trouble with common sense is not that common sense is useless. It is immensely useful in daily life. It is that common sense becomes overconfident when it tries to legislate what reality is allowed to be, at scales it was never built to comprehend. There is a certain humility required here, and physics does not always advertise humility in its tone, but the best parts of it rely on precisely that. The evidence comes first. The categories must answer to it. Electrons do not owe us classical familiarity. If they interfere, we must account for it. If they arrive locally, we must account for that too. If measurement alters which features can manifest together, we must take that seriously. The job is not to protect intuition. The job is to learn which parts of intuition survive and which parts have to be retrained. As this realization settled into physics, the natural next step was to ask what exactly the wave part means if it is not a little material ripple in the old sense. When one says the electron has a wave character, what is waving? What sort of thing spreads out, interferes, and then yields a single definite result when measured? That question led physicists toward one of the most important shifts in the whole subject. The wave, in the quantum sense, came to be understood not as a direct picture of a smeared material object, but as a way of describing probabilities, possibilities, and the structure of potential outcomes. And once that idea takes hold, the strange behaviour of electrons begins to look a little less like a contradiction and a little more like the first clear glimpse of what the quantum world is actually prepared to say. Once electrons begin behaving in ways that make interference impossible to ignore, the next question arrives almost automatically, and it is one of the most important questions in all of quantum physics. If an electron is not literally a tiny water ripple, then what exactly do we mean when we say it has a wave nature? What is waving? What spreads out? What interferes? What passes through multiple possible routes and later gives rise to a pattern of brighter and dimmer chances on a screen? That question matters because it is the point where many people either start to understand quantum theory a little better or fall into the very understandable mistake of imagining the wrong kind of wave. Classical physics had trained everyone on a fairly concrete picture. A water wave is a pattern in water. A sound wave is a pattern in air pressure. An electromagnetic wave, in the classical picture, is a pattern in electric and magnetic fields. In each case, the wave seems to be a real physical disturbance in something that extends through space. So when quantum mechanics says that an electron has an associated wave description, the first instinct is to imagine that the electron itself must be some kind of smeared out material blob, a little cloud of substance wobbling through the apparatus until it eventually decides where to land. That picture is tempting, but it becomes misleading very quickly. The reason it is misleading is that the quantum wave is not, in the usual interpretation, a wave of ordinary matter in the classical sense. It is not a tiny puddle of electron stuff sloshing about in space like spilled milk on a very expensive laboratory table. Nor is it just a visual trick with no physical meaning at all. It occupies a strange middle ground that is one of the reasons quantum theory is so successful mathematically and so awkward in ordinary language. The quantum wave is best understood as a description of possibilities, more precisely of how the probabilities for different measurement outcomes are structured and evolve. That is a sentence that sounds simple enough when one says it slowly, but it hides a major conceptual shift. In classical physics, we often use probability because we do not know enough. If I toss a coin and cover it with my hand, the coin has already landed either heads or tails. My uncertainty is a problem in me, not in the coin. Probability describes ignorance. The world itself remains definite. Something similar applies if I lose my keys. The keys are in one place. I may not know where, but the keys are not spread through the house in a mystical haze of indecision. They have a location, and I have, regrettably, failed to remember it. The quantum wave is not usually treated that way. It is not merely a summary of hidden classical facts we happen not to know. It does real work. It interferes. It evolves according to the rules of the theory. It predicts the statistical structure of repeated experiments in ways that simple ignorance about a hidden classical particle path cannot. In the double-slit experiment, for example, the wave description does not just say we are unsure which slit the electron took. It says the two possible paths contribute in a way that can reinforce or cancel, which is why the final pattern is not the same as a mere mixture of left-slit events and right-slit events. That is more than ignorance. That is a different architecture of possibility. This is why many physicists came to think of the quantum wave as a probability amplitude rather than a material wave. The exact technical phrase can sound forbidding, but the basic idea is manageable. The wave does not directly tell you what will happen in one single run of an experiment. It tells you how to calculate the relative likelihood of different outcomes when the experiment is performed. Where the wave contributions line up strongly, detections become more likely. Where they cancel, detections become less likely or nearly impossible. Over many runs, the pattern of outcomes reflects this structure. That is an important point to keep hold of because it explains how quantum theory can combine spread-out evolution with definite measurement results. The wave spreads, overlaps, and interferes in the description of possibilities. But when an actual measurement occurs, the outcome is not a mist of partial detections spread thinly over the detector. One definite result appears, one click, one spot, one electron found here and not elsewhere. The pattern only emerges when many such definite outcomes are collected. The wave guides the probabilities. The measurement delivers a single case. Now, that may sound at first like a neat solution, but it opens another difficulty immediately. If the wave is a description of possibilities, what is the status of those possibilities before measurement? Are they physically real in some meaningful sense, or are they only a calculation tool? This is where interpretation enters, and interpretation is the part of quantum mechanics where physicists often begin sounding like philosophers who have spent too long near chalkboards. Some take the wave function, the full mathematical object that encodes the quantum state, as something real in its own right. Others treat it more cautiously, as a device for organizing predictions about outcomes. Others still propose alternative frameworks in which some deeper reality underlies the wave description. The important thing for now is not to settle that debate, but to understand why it exists. The quantum wave is too effective mathematically to ignore, yet too strange conceptually to fit comfortably into familiar categories. Erwin Schrödinger played a central role in bringing this wave viewpoint into the heart of quantum mechanics. He developed a wave equation that described how the quantum state evolves over time. This was a brilliant move because it gave the new theory a precise mathematical engine. Instead of vague talk about odd behavior, physics now had a formalism that could produce concrete predictions. Schrödinger himself initially hoped that the wave might be understood in a more direct, perhaps more physically intuitive way, as though matter really were spread out in continuous form. But that hope ran into trouble, because measurements kept producing localized outcomes. Electrons in detectors do not arrive as faint fogs, they arrive as distinct events. Max Born made one of the crucial interpretive steps by proposing that the wave should be understood probabilistically, not as a literal spread of matter, but as a structure whose magnitude determines the probability of finding the particle in different places when measured. This was a major conceptual leap, and in many ways it defines the modern quantum attitude. The wave is not the particle itself in the old classical sense. It is a description of where the particle may be found and how likely different outcomes are. That proposal helped make sense of experiments without forcing the wave into the wrong physical picture. This is the point where common sense often protests that probability cannot be a real thing. It sounds too abstract, too airy, too much like a statistician trying to replace objects with spreadsheets. But quantum theory keeps insisting that probability at this level is not an afterthought. It is built into the core description. The future outcome is not simply hidden from us in the classical way. The theory itself assigns a range of possible results, with specific weights, and repeated experiments confirm those weights with extraordinary precision. Whatever else one says about the interpretation, the probabilistic structure is not a sign of weakness in the theory. It is one of its most powerful and successful features. Take the electron in an atom. In the older, classical-style picture, one might imagine it orbiting the nucleus like a tiny planet around a tiny sun. The image is charming, but it does not survive serious scrutiny. In the quantum description, the electron in an atom is represented by a wave function that occupies certain allowed forms. These forms determine the probability distribution for where the electron may be detected if one performs an appropriate measurement. That is why textbooks often show cloud-like regions around a nucleus. Those images are not pictures of a little puff of matter, permanently smeared around like cosmetic powder in zero gravity. They are visual aids for the probability structure of where the electron might be found. This distinction is vital. A probability cloud is not the same as a physical cloud. If you spray mist into a room, the mist is made of droplets that actually occupy those places. A quantum probability distribution is not made of tiny fragments of electron. It is a map of likelihood. That map can change, interfere, and evolve according to the wave equation. But when a position measurement is made, one result is obtained. Not a diluted fraction of an electron here and another fraction there. One full electron at one detected location. At this stage, people often ask whether the wave is then just in our heads, a mere bookkeeping convenience, like an accountant's ledger, or a carefully labelled drawer in a bureaucrat's office. That is too dismissive. The wave description may be probabilistic, but it is not arbitrary. It has measurable consequences even before one discusses actual outcomes. Interference effects depend on it. The probabilities from different paths combine in ways that ordinary ignorance cannot reproduce. If you treat the wave as nothing but a reflection of your lack of knowledge about some hidden definite particle path, you run into trouble explaining why the possible paths interfere. Something about the structure of the wave matters physically, even if we remain cautious about exactly how to phrase that mattering. This is why the wave in quantum mechanics is sometimes said to encode information about a system's state in a richer way than a simple classical list of properties would. It contains not just possible outcomes, but the relationships between possibilities. Those relationships are what produce interference. In a classical statistical mixture, possibilities are alternatives that merely coexist in our ignorance. In a quantum superposition, possibilities combine before measurement in a way that affects what can happen next. That is a far more subtle situation. It is one reason the quantum wave cannot be reduced to an ordinary expression of uncertainty. And then, of course, there is the awkward business of collapse, though we should approach that without theatrical thunder. In the standard textbook story, the wave evolves smoothly according to the Schrödinger equation until a measurement is made, at which point the system yields one definite outcome and the wave function is updated accordingly. This abrupt transition between smooth evolution and definite result has troubled physicists for a very long time. Does the wave genuinely collapse as a physical event? Is collapse just a change in our description once a result is known? Does the world branch in some larger structure so that every outcome occurs in a different branch, rather than one outcome eliminating the others? Different interpretations answer differently. What unites them is the recognition that the wave means something central, because the whole puzzle of measurement would not exist otherwise. It is also worth noticing that the wave concept in quantum mechanics does not belong only to electrons. Light too has a quantum state that behaves in wave-like ways in many contexts. The deeper lesson is that the wave aspect is not tied to one material kind of thing. It is part of the quantum framework itself. Both matter and radiation are described through states that can exhibit superposition and interference. That is one of the reasons the old distinction between waves and particles becomes less and less helpful the farther one moves into quantum theory. The wave aspect is not the private property of light. It is part of the grammar of the quantum world. Still, even as we say that, we must avoid a new oversimplification. The phrase, "everything is a wave," can become just as misleading as the phrase, "everything is a particle." It encourages the wrong mental picture if one forgets what sort of wave is meant. Not a classical water wave, not a smear of hidden substance, not a polite vibration of some familiar medium. The quantum wave is a mathematical description of possible outcomes and their relations, capable of interference, capable of predicting distributions, and somehow linked to definite measured events that emerge one at a time. That is not the kind of thing ordinary language was designed to handle elegantly. This is why quantum mechanics so often feels as though it is forever one translation short of comfort. The mathematics says something precise, the laboratory confirms it, but the verbal paraphrase is always at risk of misleading us. Say the electron is a wave and people imagine a literal spread of matter. Say the wave represents probabilities and people imagine mere ignorance. Say the wave is real and people ask why it produces one localized result. Say it is only a tool and people ask why its interference structure matters so much physically. Every sentence helps a little and distorts a little. The best one can do is move carefully and keep the experimental facts in view. One of the more humbling things about this is that nature does not appear to mind our discomfort. Atoms remain stable, semiconductors continue working, lasers operate, chemical bonds hold. All of this depends on the quantum description succeeding where classical ideas fail. The wave meaning in quantum mechanics is not a decorative interpretation added after the real work is done. It is built into the success of the theory across enormous stretches of modern physics. If we want electronics, chemistry, material science, and a great deal else besides, we have to live with the fact that the world seems to traffic in this peculiar probability wave structure, whether or not it flatters our old intuitions. There is a useful way to think about the shift, though it requires a little patience. In classical physics, one often begins with objects and then describes what they do. In quantum physics, one often begins with the state and then asks what outcomes become available under a given measurement. That is a different order of thinking. The state is not simply a list of hidden object properties waiting to be uncovered. It is the full quantum description from which probabilities for various measurements are derived. That is why different measurements can reveal different aspects, and why not all classical properties can be assigned simultaneously in the way we might wish. The wave encodes more than a single, tidy story about where the object is and what it is doing when nobody is looking. This is also where one begins to see why wave and particle are not true identities in the deep quantum sense. The wave description tells you about the evolving structure of possibilities. The particle-like aspect appears in the discrete, localized character of certain interactions and measurements. These are not two complete portraits of a hidden classical object. They are two limited windows onto different features of a deeper quantum reality. Once that is grasped, even imperfectly, the old question starts to loosen its grip. The goal is no longer to decide which classical label wins. The goal is to understand what role each label plays and where each one stops being trustworthy. And that inevitably brings us to the next difficulty. If the quantum wave describes possibilities and probabilities, how do those possibilities become one definite actual event? How does the spread of potential outcomes give way to a single click here rather than there? Why does measurement seem to have this peculiar power to produce one answer out of many allowed ones? That is where the calm mathematical story begins to collide with one of the most controversial parts of the whole subject, because the act of measurement is not merely a passive glance at an already finished world. It appears to be part of the process by which a single definite outcome enters the record at all. There is a habit in everyday life of treating measurement as something gentle. You take the temperature of a room, you weigh a piece of fruit, you glance at the time, you check whether it is raining. In all of these cases, measurement feels like a polite form of noticing. The world is already doing whatever it is doing. and you simply look in, take note and move on. Perhaps you disturb things a little if you're clumsy, but the basic idea remains intact. A ruler does not appear to bully the table into having a length. A bathroom scale may offend your mood, but it does not seem to create your mass out of thin air. In ordinary life, measurement feels passive, almost courteous. Quantum physics does not grant us that comfort. At the quantum level, measurement is not merely a glance. It is an interaction, and often a rather rough one. To measure where an electron is, or which path it took, or what energy it has, the system must be coupled to something else, some apparatus, some physical process, some mechanism capable of leaving a record. And the moment that coupling becomes strong enough to produce a definite result, the quiet spread of quantum possibilities is no longer left alone. The system does not simply reveal itself untouched. It is drawn into an encounter that changes what can meaningfully be said about it afterward. That is why measurement in quantum mechanics has such a dramatic reputation. It is not because physicists enjoy sounding mysterious. It is because the act of obtaining a definite answer seems bound up with a real physical disturbance to the prior quantum state. This is what I mean by the quiet violence of measurement. Not violence in the melodramatic sense, as though detectors are staging tiny crimes against particles in darkened laboratories, but violence in the deeper sense that something delicate is being broken. Before measurement, the quantum state can carry multiple possibilities in superposition. Different paths can contribute. Different outcomes can remain available in a single unified description. Interference can occur because those alternatives have not yet been forced apart into distinct recorded facts. Measurement, when it succeeds, destroys that delicacy, turns a spread of structured possibilities into one actual registered result. It breaks the coherence that allowed the wave-like description to do its subtle work. That word coherence matters a great deal here. Coherence refers to the stable phase relationships between different parts of a quantum state, the very relationships that allow interference to happen. If those relationships remain intact, the system behaves in the fully quantum way we've been discussing. Possibilities can reinforce or cancel, but once the system interacts with an environment or apparatus in a way that distinguishes those possibilities, coherence is lost. The alternatives no longer combine cleanly. They become effectively separate, and when that happens, the quantum pattern of interference disappears, and a more classical-looking outcome begins to emerge. This is why, in the double-slit experiment, the mere possibility of obtaining which path information can destroy the interference pattern. It is not that the electron is offended by curiosity. It is that the physical setup required to determine the path necessarily entangles the electron with some other system. The path alternatives become correlated with distinguishable states of the detector or environment. Once that correlation exists, the clean interference between the alternatives is no longer available in the same way. The wave-like pattern gives way to something more like a classical mixture of options. The quiet coherence has been interrupted by the hard fact of record-making. And that phrase record-making may be one of the most useful ways to think about measurement. A measurement is not just a microscopic nudge. It is an interaction that leaves behind a stable macroscopic consequence, something that can in principle be read, remembered, or amplified. A tiny event becomes a detector click, a flash on a screen, a mark on a photographic plate, a current pulse in a circuit, a trail in a chamber. The microscopic quantum world meets the larger world of persistent facts. The result must become robust enough that it no longer behaves like a fragile superposition of alternatives. It must become this rather than that, a result you can write down, a result another person can verify, a result that enters the ordinary world of shared observation. That transition is much stranger than it sounds. In classical physics, one would say the measurement device simply uncovers what was already true. The particle was already here. The energy already had that value. The path was already left rather than right. The apparatus merely reveals the hidden fact. Quantum mechanics complicates that story. because the state before measurement often does not seem to assign one such definite classical value in the ordinary way. Instead, it provides a structured range of possibilities. So when the apparatus produces one definite answer, the natural question becomes unavoidable. Where exactly did the single outcome come from? Was it always there in some hidden form? Did the act of measurement select it? Did the interaction with the apparatus create the conditions under which the question itself finally became definite? These are not trivial questions, and physics has not settled them in one universally accepted interpretation. That is important to say plainly. The mathematics of quantum mechanics tells us extremely well how to calculate the probabilities of outcomes and how the quantum state evolves prior to measurement. But the deeper conceptual story of why one result appears rather than the full cloud of alternatives is where the famous measurement problem lives. Different interpretations offer different answers. Some speak of collapse as a real physical process. Some treat the apparent collapse as an update in our description once information is obtained. Some propose branching worlds in which every outcome occurs, though any one observer experiences only one branch. Others seek hidden variables or altered dynamics. The variety of interpretations is not a sign that the experiments are unclear. It is a sign that the experiments are clear enough to force the problem into view, while the conceptual resolution remains contested. Still, for all that controversy, a few things can be said with confidence. Measurement is physical. It is not magic. It does not require a human mind to stare intensely at an electron like a stern librarian. Consciousness is often dragged into popular discussions of quantum theory because people hear that observation matters and assume that means awareness itself changes reality. That is usually not the right lesson. What matters in the laboratory is interaction, amplification, irreversibility, the building of a record. A detector does not need to be emotionally invested in the outcome. It only needs to couple to the system in a way that produces distinguishable states. The Geiger counter clicks whether or not anyone is feeling philosophical about it. This is one of the reasons the word observation can be misleading. In daily life, observation sounds mental. In quantum physics, it is better understood physically. A system is measured when it becomes correlated with another system that serves as an apparatus or environment, and when that correlation is amplified enough to produce a stable fact-like result. The human observer enters later, reading the instrument. The drama has already happened in the hardware. Long before anyone looks at the screen and murmurs something thoughtful, the delicate quantum coherence has often already been scattered into the world. Consider a photographic plate exposed to very weak light. If the light behaves quantum mechanically, the plate does not develop as one uniform smear from a single photon being half everywhere in the classical sense. Instead, individual localized marks appear one by one, and after many such events the familiar distribution emerges. Each mark corresponds to a discrete interaction in the material of the plate. The incoming quantum state may have spread its probabilities widely, but the measurement event itself results in one localized consequence. The plate becomes part of the story. Its atoms, its chemistry, its ability to preserve or trace all matter. Measurement is not abstract bookkeeping. It is an event that propagates from microscopic interaction into macroscopic permanence. Cloud chambers and bubble chambers make this vividly visible. A charged particle moving through such a device leaves behind a trail of droplets or bubbles. The track looks almost comfortingly classical, as though the particle has kindly returned to the familiar world of paths and positions. But that visible line is the result of many localized interactions, each one forcing a bit of microscopic possibility into a definite record. The apparatus is continuously measuring the particle through its effects on the surrounding medium. What looks like a smooth trajectory at large scale is built from a chain of quantum events that have been amplified into something our ordinary eyes can follow. In a way, the chamber is domestication. It takes the elusive quantum behavior and forces it into a succession of stable marks that resemble a classical history. That resemblance, however, should not fool us into thinking the underlying issue has disappeared. A measurement device can make a quantum system look classical by destroying the coherence between alternatives, but explaining why one particular result rather than another becomes actual remains subtle. This is where the word decoherence enters the story, and it is one of the most important ideas in modern discussions of measurement. Decoherence describes the loss of coherent phase relations when a quantum system interacts with its environment. Imagine a system that could in principle be in a superposition of alternatives. If it remains isolated, those alternatives may continue to interfere, but if the system becomes entangled with countless environmental degrees of freedom, air molecules, photons, vibrations, thermal noise, stray interactions of every sort, then the delicate relationships needed for interference effectively disperse into the environment. The system no longer behaves as a clean, isolated superposition from the point of view of accessible observation. It begins to look like a classical mixture. Decoherence explains why macroscopic objects do not typically display obvious quantum interference in daily life. They are never isolated well enough. The environment is constantly monitoring them, in a loose but relentless sense. This is a profound insight because it shows how the classical world can emerge from the quantum one without requiring a mysterious line painted across nature. Chairs do not display visible superpositions, not because chairs are exempt from quantum rules, but because a chair is an enormous, warm, complicated system endlessly interacting with its surroundings. The coherence between macroscopically different chair states is destroyed almost unimaginably quickly. The world we inhabit is saturated with environmental measurement. Light scatters, air collides, heat flows, surfaces vibrate. The environment is an enthusiastic gossip. It keeps gathering information and smearing delicate quantum relationships into practical irretrievability. Yet decoherence, for all its power, does not fully solve the whole measurement problem. This is an important point that sometimes gets blurred. Decoherence explains why interference between alternatives becomes inaccessible and why systems begin to behave classically for practical purposes. It tells us why we do not see absurd superpositions in ordinary experience. But by itself, it does not necessarily explain why one single outcome is experienced rather than the full spread. It transforms a pure coherent superposition into something that behaves like a mixture from the perspective of local observers, but the deeper question of actual definiteness still depends on interpretation. Does one branch become real for us because of collapse? Do all branches remain in a larger structure? Is there some hidden mechanism that selects one? Decoherence narrows the mystery. It does not eliminate it entirely. There is something almost paradoxical about this. Measurement feels so ordinary, we live by it. Thermometers, watches, clocks, rulers, cameras, sensors, maps, receipts, train timetables, all the little devices by which life is pinned down and coordinated. Yet one of the deepest open conceptual problems in physics concerns how a measurement yields a definite result at all. The modern world runs on instruments whose operation depends on quantum mechanics, while the interpretation of their most basic act remains partly unresolved. That is not a weakness of the technology. It is a reminder that successful use and final understanding are not always the same thing. It also changes the emotional tone of what it means to know something. In classical thinking, knowledge is passive discovery. In quantum thinking, knowledge is entangled with intervention. To know the path, you must introduce a path-sensitive interaction. To know the position more precisely, you must couple in a way that localizes the system, often disturbing complementary features. To register a result, you must allow the microscopic delicacy to be amplified into macroscopic fact. Knowledge here is not plucking fruit from a tree that was already hanging there unchanged. It is more like pressing a seal into warm wax. Something is made definite by the process that reveals it. This is why measurement carries that curious mix of quietness and violence. It is quiet because the apparatus may sit there humming gently, clicking politely, displaying numbers with no sign of drama. The laboratory can look almost boring. A detector screen glowing softly in the dark does not exactly scream metaphysical crisis. But it is violent because every definite outcome means a coherent spread of alternatives has been reduced, disrupted, or rendered inaccessible. A possibility space has been forced into one fact. A fragile quantum condition has been dragged into the blunt world of records. The bluntness of records matters more than one might first think. A measurement result is something that can be copied, communicated, and made durable. That durability is central to classical reality as we experience it. When you look at a table, light from the table reaches your eyes, your nervous system responds, memory updates. Perhaps someone else sees the same table, perhaps a camera records it, perhaps the table casts a shadow and resists being walked through. The world of ordinary objects is one of massively redundant records. The environment continuously spreads information about macroscopic states. That redundancy helps make facts stable. Quantum superpositions do not survive easily once information about them has leaked everywhere. In a sense, reality becomes classical where records become robust and widely shared. That thought can sound abstract, but it explains a good deal about why the world feels the way it does. You do not live in a silent vacuum of isolated quantum systems. You live in a torrent of interactions. The sunlight in a room, the warmth of objects, the collisions of air molecules, the constant exchange of information between systems and surroundings all contribute to a world in which definite appearances dominate. The macroscopic world is what happens when measurement, in the broad physical sense, is everywhere all the time. Still, one should resist the temptation to think this reduces the mystery to mere practical inconvenience. The deeper question remains hauntingly simple. Why this outcome? Why this click rather than that one? Quantum theory gives probabilities, and over many trials those probabilities prove astonishingly reliable. But for the individual event, the transition from possibility to actuality retains its peculiar abruptness. The theory tells you the weights of the possibilities. It does not, in the standard interpretation, tell you why this particular run gave the result you just saw. That gap is one reason probability becomes so central to the quantum view. The theory is not a story about certainty hidden under ignorance in the old way. It is a theory in which uncertainty is woven into what can be predicted before measurement takes place. And once one accepts that, another question naturally follows. If measurement draws definite outcomes from a field of possibilities, what exactly can be said in advance? How sharply can those probabilities be structured? What limits does the theory place on prediction? How does uncertainty itself become not just a flaw in our instruments, but part of the shape of the invisible world? That is the road ahead, because once measurement has done its quiet damage and left one fact standing where many possibilities once were, the next thing physics must teach us is how those possibilities were weighted in the first place, and why certainty at the quantum scale comes wrapped in probabilities rather than guarantees. Once measurement has entered the story and turned a spread of possibilities into one recorded fact, another question begins to press forward almost immediately. If the quantum world does not hand us certainty in the old classical way, then what exactly does it give instead? What can we know in advance, and what are the limits on that knowledge? When a theory describes not one inevitable future, but a structured range of possible outcomes, how should we think about probability? And when physicists speak of uncertainty, are they simply confessing that their instruments are imperfect, or are they pointing to something deeper built into the world itself? This is where quantum physics becomes especially difficult for common sense, because it asks us to take probability more seriously than we usually like to. In daily life, probability often feels like a practical compromise. We use it when the full details are too numerous, too hidden, or too annoying to track. If someone asks whether it will rain tomorrow, we may speak in probabilities because the weather is complicated. If you roll a die, you speak in probabilities because you do not know the exact forces and angles well enough to predict the outcome. If you shuffle cards, you use probability because the arrangement is hidden from you. In all of these cases, probability stands in for incomplete information. The world itself is assumed to be definite. The die lands on one face because of the physical conditions. The clouds either will or will not produce rain because the atmosphere will evolve in one way rather than another. Probability reflects our ignorance, not the inner style of reality. Quantum mechanics unsettles that comforting distinction. In the quantum world, probability is not simply a temporary patch for ignorance in the old classical sense. It is built into the theory at a much deeper level. The wave description gives not a list of hidden definite properties waiting quietly behind the curtain, but a structure of possible outcomes with different weights. When a measurement is made, one outcome appears, but before that happens, the theory does not in general assign a single classical result already sitting there in plain form. It assigns a pattern of likelihoods. This is not the same as saying physics knows nothing. Quite the opposite. Quantum theory knows an extraordinary amount. It can tell you the probability distribution with astonishing precision. It can tell you how that distribution changes over time. It can tell you which outcomes are more likely, which are less likely, and which are effectively forbidden. What it often does not give you is one guaranteed result for an individual event. That can sound weak at first, until you notice how successful it is. Repeated quantum experiments follow these probability rules with extraordinary reliability. If you prepare the same system again and again under the same conditions, the distribution of results matches the predictions of the theory with remarkable accuracy. One electron lands here, another there, another somewhere else. No single event may be certain in advance, yet the pattern of many events is structured with an almost unnerving faithfulness. Quantum probability is not vague guessing, it is disciplined uncertainty. There is something both unsettling and beautiful about that. The world at small scales appears not as a hidden machine whose every detail is there if only we could pry hard enough, but as a domain where the possible has shape. That shape matters. It is measurable. It is lawful. It is not chaos. But it is not certainty in the classical sense either. It is a geometry of likelihood, a contour map of where reality is more willing and less willing to deliver particular outcomes. This is one reason the language of the invisible becomes so important. We cannot usually watch quantum systems directly in the way we watch a stone thrown across a field. We infer, calculate, and measure through apparatus. The underlying state is invisible in the ordinary sense, yet it has form. Not visual form as a little object with edges perhaps, but mathematical form that determines the structure of possible results. When people speak of the shape of the invisible in quantum mechanics, this is often what they mean. The wave function, or quantum state more broadly, gives a patterned description of possibilities. It tells us how likely different measurements are to turn out in different ways. It has peaks, troughs, symmetries, and restrictions. It is invisible to the eye, but not formless. Think of an electron bound in an atom. If one clings to the old classical image, one might expect the electron to move around the nucleus in a little orbit, perhaps like a miniature planet. But the quantum description replaces that tidy path with a set of allowed states, each with its own probability pattern. Some regions are more likely for a detection, others are less likely. In certain states there are even regions where the probability of finding the electron drops to nearly nothing. That is not a matter of the electron physically avoiding those regions because it dislikes the scenery. It is part of the structure of the quantum state itself. The invisible has shape, and that shape governs what can happen. This is also where uncertainty becomes more than a complaint about inadequate tools. The most famous expression of this is associated with Werner Heisenberg, whose name is now permanently tied to the uncertainty principle. In popular culture, this idea is often turned into a vague claim that everything is fuzzy, or that measurement disturbs reality so much that nothing can ever be known. That is not quite right, and it is worth slowing down because the actual lesson is both more precise and more interesting. The uncertainty principle says, roughly speaking, that certain pairs of physical quantities cannot both be made arbitrarily sharp at the same time within the quantum description. The better defined one becomes, the less sharply the other can be. The most famous pair is position and momentum, meaning roughly location and motion. If a quantum state is arranged so that position is very narrowly localized, then the range of possible momenta becomes more spread out. If momentum is very sharply defined, the position becomes more spread out. This is not merely a practical problem caused by clumsy instruments bumping into tiny objects. Though measurement disturbance is certainly part of the story in some contexts, it is built into the structure of the quantum state itself. That is a profoundly different claim from ordinary ignorance. In classical physics, an object can in principle possess both an exact position and an exact momentum at the same time, even if no one knows them. The uncertainty is only in the observer. In quantum mechanics, the theory does not generally permit a state in which both are simultaneously sharp beyond a certain limit. The blur is not simply in our minds, it belongs to the shape of the state. One useful way to picture this without slipping into the wrong sort of literal image is to think of localization as requiring a tighter packet in space. But a tighter packet in space is built from a wider spread of motion-related components. A more definite place comes with a less definite range of movement. The details are mathematical, but the lesson is physical. Sharpness in one direction comes at the expense of sharpness in another. The invisible world has built-in trade-offs. This can feel almost rude from the point of view of ordinary reason. We're used to imagining that if something exists, then all its properties ought to be there waiting for us in complete detail. But quantum mechanics keeps saying no, not always in the way you mean. Some features of a system are not jointly available with unlimited precision, because the state itself cannot support that arrangement. Reality at this scale is not a filing cabinet in which every drawer can be opened fully at once without the contents shifting. And yet, once again, this is not a story of failure. It is a story of structure. The uncertainty principle is not a declaration that nature is hopelessly vague. It is a declaration that the invisible world is organized according to rules different from those suggested by common sense. There are patterns of possibility, not unlimited simultaneous definiteness. There are constraints, but they are intelligible constraints. They show up in the stability of atoms, in the behavior of electrons in matter, in the limits of confinement, in countless features of quantum systems. The principle is strange, yes, but it is not random. It is one of the ways the hidden architecture of the world reveals itself. Probability and uncertainty also become unavoidable when one considers decay and emission processes. A radioactive atom does not come with a little internal timer that says it will definitely decay at this exact instant on Thursday afternoon just after tea. Instead, quantum theory assigns probabilities. There may be a characteristic rate, a typical behavior across many atoms, a reliable statistical pattern for how large groups will decay over time. But for any one individual atom, the exact moment of decay is not predicted with certainty. The theory gives a distribution of likelihood. This is another case where people sometimes feel cheated. They want the atom to have a secret schedule. Quantum mechanics declines to provide one, at least not in its standard form, and still the statistical predictions are so successful that modern technology and experimental science rely on them confidently. This is one of the recurring lessons of quantum theory. We do not always get certainty about individual events, but we get extraordinarily reliable knowledge about distributions. The shape of the invisible is not a single path but a weighted field of possibilities. The same goes for tunneling, one of the most astonishing consequences of quantum probability. In classical physics, if a particle does not have enough energy to get over a barrier, then that is that. The barrier wins. The particle remains on its side, perhaps with a sense of disappointment. In quantum mechanics, the wave description allows there to be a non-zero probability of finding the particle on the other side of the barrier, even when classical reasoning would forbid it. This is not because the particle somehow borrows determination or sneaks through while the laws are distracted. It is because the probability wave extends into and beyond the classically forbidden region. Most of the time, the barrier still does what barriers do, but not always. Sometimes the invisible shape of possibility reaches farther than classical logic would permit. This effect is not a tiny curiosity filed away in the back of the theory. It plays a role in real physical processes. It helps explain certain kinds of radioactive decay. It matters in the operation of scanning tunneling microscopes. It contributes to behavior in semiconductors and other modern devices. The impossible becomes possible in carefully weighted amounts. Again, the point is not that quantum mechanics abolishes order. It redefines what lawful order looks like. There is also a broader psychological lesson here. Human beings are quite attached to the idea that the invisible should resemble the visible once reduced far enough. We imagine that if only we could zoom in, the hidden world would be like ours but smaller, cleaner, and perhaps more annoying to clean. Quantum theory refuses this. The invisible is not simply miniature furniture. It has its own grammar. Probability is not a temporary stain on knowledge waiting to be scrubbed off. Uncertainty is not merely a sign of poor craftsmanship. The hidden world is not less real because it is not classically definite. It is more subtle. This subtlety becomes especially clear in the way probabilities can interfere. In ordinary statistical reasoning, one often has alternative possibilities that simply add. If a classical object can arrive by route 1 or route 2, and the routes are independent alternatives, the total chance is the sum of the separate chances. But in quantum mechanics, the amplitudes associated with those alternatives combine first, and only then do probabilities emerge. This is why interference patterns exist at all. It means the invisible does not merely contain multiple options. It contains relationships between options that shape the final outcomes. The possible is not just listed, it is organized. That organization is why the word shape is so apt. A quantum state is not merely a bag of potential events rattling around at random. It has contour, it has symmetry, it has nodes and peaks and patterns. In atoms, molecules, crystals, fields, and devices, these shapes determine what can happen. Electrons occupy allowed arrangements because the quantum state supports certain structured possibilities and not others. Chemical bonds arise because these invisible shapes fit together in particular ways. Materials conduct or insulate because of how quantum states are distributed in them. The world we touch is built partly out of patterns we never directly see. It is worth pausing on that because it makes the whole topic feel less like philosophical haze and more like physical reality. The invisible in quantum mechanics is not a retreat from the real. It is a deeper layer of organization from which many visible realities emerge. The smooth hardness of a table, the color of a metal surface, the operation of a transistor, the emission of light from a laser, the structure of a molecule in your body, all of these depend on quantum probabilities having exactly the shape they do. If those invisible patterns were different, ordinary reality would be different as well, and this brings us back to the question of certainty. Classical physics encouraged the hope that if we knew enough, we could predict everything with absolute specificity. Quantum mechanics asks us to lower that ambition in one sense and raise it in another. We may not get the exact individual outcome every time, but we gain a theory that tells us the structured range of outcomes with astonishing power. The uncertainty is not a failure of science to become precise. It is part of what precision means at this level. A precise quantum statement is often a probabilistic one. That can take time to accept because certainty feels emotionally safer than probability. We like the world to seem firmly arranged, like books on a shelf or trains on a timetable. Probability feels slippery. Yet much of life already runs on structured uncertainty. Weather forecasting, insurance, medicine, traffic, public health all rely on patterns that are statistical rather than individually guaranteed. Quantum mechanics takes this one step deeper and says that the physical world itself, at the smallest scales, is described in terms of such structured likelihoods, not because science has given up, but because this is what repeated experiment demands. There is even something strangely mature about that lesson. It asks us to distinguish between predictability and intelligibility. A world can fail to give exact certainty about each event and still be intelligible through lawful patterns. Indeed, that may be the more accurate picture of reality. We are not owed a universe that behaves like clockwork merely because clocks are convenient. Still, the old language keeps tugging at us. If the invisible is shaped by probability and constrained by uncertainty, if the wave is a map of possibilities and measurement yields one actual result, then what sort of thing are we really talking about? Is it a wave? Is it a particle? Or are those words becoming less helpful the more seriously we take the evidence? By now the answer is beginning to come into view. The classical identities are starting to look not false exactly, but incomplete. They are like familiar tools used beyond the conditions they were made for, useful up to a point, misleading beyond it. And so the story naturally begins to move toward its next step. Once probability has replaced certainty, and the invisible has revealed itself as structured but not classically definite, it becomes harder and harder to believe that wave and particle are the final categories. They start to look more like partial glimpses, each catching something real, neither exhausting the thing itself. The deeper task now is not to keep choosing between them, but to ask what lies beneath both labels and why quantum reality seems content to let each of them work only part of the time. By this point, the old question has started to feel a little too small for the evidence it was meant to organise. Is it a wave or a particle? At the beginning, that sounded like a perfectly respectable thing to ask. It sounded clear. It sounded disciplined. It sounded like the sort of question physics ought to reward. After all, waves and particles had seemed for so long like two different kinds of behaviour belonging to two different kinds of thing. Waves spread, interfere, overlap, and bend. Particles arrive, collide, count, and localize. If light and matter were showing signs of both, then surely the task was simply to determine which identity was the true one underneath the confusion. But the further quantum physics developed, the more that hope began to weaken. Not because the evidence became muddier, but because it became more precise. The very experiments that were supposed to help us settle the matter instead revealed something more troublesome. The wave picture explained interference, diffraction, and the structured spread of probabilities. The particle picture explained discrete detections, local interactions, and countable transfers of energy. Each picture worked strikingly well in the situations where it applied, and yet neither picture could stretch far enough to become the whole truth, without tearing somewhere important. That is the point at which physics begins to do something both frustrating and admirable. It stops pretending that the old categories are sacred. There is a temptation in science, as in life, to keep polishing familiar ideas long after they have stopped fitting the world. We all do this in our own ways. We keep old labels because they once helped us. We keep old habits because they once worked. We keep old explanations because they still feel comfortable even when reality has quietly moved on. Quantum theory, for all its oddness, was one of the moments in science when comfort had to be sacrificed to accuracy. Wave and particle did not disappear, but they were demoted. They stopped being final identities and became limited descriptions, useful in context, misleading when overextended. That shift can sound more abstract than it really is, so it helps to be very plain about what changed. When physicists say that a quantum object is beyond wave and particle, they do not mean it is some mystical goo that obeys no rules and laughs at logic. They do not mean it is undefined or magical or made of pure contradiction. What they mean is more disciplined than that. They mean the underlying quantum entity is described by a framework in which wave-like and particle-like features appear under different conditions, but the entity itself is not identical to either classical concept taken on its own. Those concepts survive as approximations, not as foundations. In a way, this is not as strange as it first sounds. Science has done this kind of thing before. There are many cases where everyday categories turn out to be too crude once a field matures. Heat once seemed like a substance to some thinkers, something that could flow from one body to another as a kind of material fluid. Later, it was understood in terms of molecular motion and energy transfer. The old language had captured something real enough to be useful, but it was not the deeper account. Likewise, solidity feels simple in daily life, but modern physics tells us that what we call a solid object is mostly empty space structured by fields, forces and quantum states. The ordinary description still works at our scale. It is not nonsense. It is just not the deepest level of explanation. Wave and particle in the quantum story have undergone something similar. They remain indispensable pieces of language. One cannot do without them altogether, because experiments keep displaying behaviours that fit those classical families in important ways. But once quantum mechanics is taken seriously, the real explanatory work is no longer being done by those old labels themselves. It is being done by the quantum state, by operators associated with measurements, by amplitudes, probabilities, and the structure of possible outcomes. The classical words become summaries of what certain measurements and situations make visible. This is why the question of what a quantum object really is becomes so slippery. If one asks for a visual image in the old style the theory resists, it does not hand over a tiny literal picture of an electron as a little ball with a secret ripple attached, nor as a tiny wave with a hidden hard core. Instead, it offers a state description that evolves according to precise rules and yields probabilities for measurements. It gives you the machinery for prediction without always satisfying the older hunger for a single mechanical picture. That gap between predictive power and visual intuition is one of the signatures of the quantum world. It is also one reason why Niels Bohr's idea of complementarity became so influential. Bohr argued in effect that wave and particle descriptions are complementary, rather than mutually exclusive in the ordinary sense. Each captures something real about the phenomena, but not at the same time in the same classical way. The experimental arrangement determines which aspect can be manifested clearly. In one context, the wave description becomes essential. In another, the particle description is unavoidable. Trying to force both into simultaneous classical completeness leads to confusion, because the concepts themselves belong to a scale of experience for which quantum conditions were never designed. Bohr's view has sometimes been criticised for sounding evasive, and perhaps it can sound that way if stated too briefly. But its strength lies in its honesty. It refuses to pretend that one classical image can be stretched to cover all the facts. It accepts that the language of observation is inherited from the macroscopic world, and therefore what we say about quantum systems must always pass through concepts that are not native to the deepest level of the theory. That is not ideal if one prefers pictures to be complete, but it may be the price of speaking at all. There is another way to feel the inadequacy of the old categories, and that is to notice how thoroughly modern quantum theory has moved beyond them in practice. Physicists no longer spend their working days asking whether an electron is secretly more wave or more particle in the crude old sense. They calculate states, scattering amplitudes, transition probabilities, energy levels, correlations, and fields. They build devices, interpret data, and design experiments using the formalism that has proved itself again and again. The theory is not centered on a permanent identity card that says wave or particle. It is centered on what the state is, how it evolves, and what different measurements can reveal. Even the concept of the particle becomes more subtle in advanced theory. In quantum field theory, which is the framework that underlies much of modern particle physics, the basic objects are not tiny billiard balls moving through empty space in the old classical style. Instead, fields are central, and what we call particles can be understood as quantized excitations of those fields. That is already a very different picture from the older particle intuition. A photon is not a little pellet of light drifting through space like a microscopic bead. An electron is not simply a hard miniature marble. Each is an excitation associated with a field, and the details of what counts as a particle can even depend on the context in ways that would have seemed outrageous to classical intuition. Now, one must be careful here not to swap one oversimplification for another. Saying that everything is really a field can be just as misleading as saying everything is really a particle or really a wave if one hears the words too casually. Classical fields carry their own baggage of continuous spread and smooth behaviour. while quantum fields inherit the same strange mixture of discreteness and probability that has been troubling us all along. Still, the move to quantum field theory makes one thing plain. The foundational structures of modern physics are not built by choosing once and for all between classical wave stuff and classical particle stuff. They are built from a deeper framework in which both familiar modes of description arise under suitable conditions. This is one of the places where language starts to show its seams. The word particle survives because it remains useful in many experiments. Detectors click as though something localized arrived. Energy and momentum come in quantized exchanges. Tracks form in chambers. Scattering events can often be analyzed as though particles were entering and leaving the scene. The word wave survives because states spread, interfere, diffract, and combine in ways that demand wave mathematics. But these words are now more like handles than final portraits. They give you something to grip while working with the theory, but they do not exhaust what the theory is talking about. There is something almost modest in that. The deeper lesson of quantum mechanics may not be that reality is absurd, but that the concepts formed from everyday life do not get the last word. That is humbling, though perhaps it should not be shocking. Why should the habits of a medium-sized primate on one planet be the final measure of what can exist? Our brains were shaped to notice fruit, faces, cliffs, weather, movement, and danger. They were not built to offer native intuition about Hilbert spaces, superpositions, or quantized fields. It is already rather generous of the universe that mathematics lets us get as far as it does, and yet we should not make the mistake of treating beyond wave and particle as a fancy way of saying nobody understands anything. That would be too dramatic, and also simply false. Physicists understand a tremendous amount about quantum systems. They know how to calculate spectra, scattering rates, tunneling probabilities, correlations, interference patterns, and countless other measurable phenomena with extraordinary accuracy. Modern technology depends on this. The issue is not that the theory lacks structure. The issue is that the structure is not naturally expressed in the old visual language of classical objects. Prediction outran analogy. That distinction matters because there is a common temptation to think that if something cannot be pictured simply, it must not be properly understood. But understanding comes in more than one form. Sometimes it means possessing a vivid mechanical image. Sometimes it means having a robust mathematical framework that links preparation, evolution, and measurement with reliable precision. Quantum mechanics gives us the second in abundance, even when the first remains partial. That can feel unsatisfying if one longs for a small-scale movie one could run in the mind. But perhaps the longing itself is part of the problem. We keep asking the world to resemble a kind of understanding that happens to suit our brains. The further one goes, the more the question becomes not what label to pin on the object, but what structure of reality gives rise to these context-dependent appearances. Why does the world allow interference in one experimental arrangement and localized countable outcomes in another? Why do probabilities have the form they do? Why do certain observables fail to become simultaneously sharp? Why do some states behave more classically than others? These are richer questions than the old either-or, because they take the quantum framework on its own terms rather than demanding that it behave like a slightly eccentric version of classical mechanics. There is also a kind of maturity in accepting that explanation sometimes means replacing the question, rather than answering it in the form first asked. Children often ask why the sky is blue, in a way that expects a simple descriptive answer, and then physics slowly teaches them about scattering wavelengths and atmospheric conditions. The original question was good, but the final answer is not framed in the same ordinary terms the question first implied. Something similar happens here. Is it a wave or a particle was a good opening question because it captured a real tension in the evidence. But the quantum answer comes by changing the framework, so that the classical alternatives are no longer the deepest possibilities on the table. One can even see this in the way experiments are now designed at the frontier of the subject. physicists create superpositions of increasingly large systems, preserve coherence with extraordinary care, manipulate entanglement, and build quantum computers that rely not on classical particle paths or classical waves alone, but on the distinctive logic of quantum states. The practical future of the field lies not in deciding once and for all whether electrons should sit in the wave box or the particle box, but in learning how to control the deeper structure that made those boxes insufficient to begin with. Entanglement is especially revealing in this regard. When quantum systems become entangled, the state of the whole cannot be reduced neatly to independent properties of the parts. Correlations appear that no classical picture of separate little objects with pre-existing individual states fully captures. This pushes the lesson beyond the wave-particle debate into a wider transformation. Not only are the categories of wave and particle limited, but the very idea of isolated things with fully self-contained classical properties begins to loosen. Reality at the quantum level can be relational, structured by joint states and correlations that are deeper than ordinary separateness. That is one reason the phrase deeper quantum reality is not just decorative language. It points to the fact that wave and particle are surface-level descriptions of manifestations, not the full ontology of the theory. What lies beneath may be states, fields, amplitudes, symmetries, and relations that give rise to the familiar appearances under specific measurement conditions. We're not merely failing to choose the correct side in an old debate. We are discovering that the debate itself belonged to a shallower layer of understanding. Of course, one can still ask whether there is some future theory that will make everything feel intuitive again. Perhaps. Science has surprised itself before. It is conceivable that a more complete framework will one day place quantum theory inside an even larger account that gives clearer conceptual footing. But even if that happens, it is hard to imagine the future simply restoring classical wave and particle as final primitive categories. Too much evidence has piled up against that hope. Any deeper theory will have to explain why both descriptions work when they do, fail when they do, and emerge as approximations from something more general. And that may be the key word here: emergence. Much of physics progresses by showing how familiar concepts emerge from deeper structures under particular conditions. Temperature emerges from statistical behavior of many particles. Solidity emerges from fields and forces. Classical trajectories emerge approximately when decoherence and scale suppress quantum interference. Wave and particle may belong to that same family of emergent descriptions. They are not lies. They are macroscopic or context-specific ways reality presents itself when certain features dominate and others become negligible. The mistake is only in asking them to be universal. So by now, the answer to the old question has changed in tone: wave or particle. Neither, if by those words you mean complete classical identities. Both, if by those words you mean limited descriptions of different aspects of quantum behavior under different conditions. But even that both is only a halfway house. The more careful answer is that the quantum world is built from something whose behavior gives rise to wave-like and particle-like manifestations, without itself being reducible to either familiar image. The deeper theory is not indecisive, it is simply not classical. There is a certain relief in that once one stops fighting it. The puzzle becomes less about choosing sides and more about learning a new grammar. The world is not teasing us by switching costumes. It is inviting us, rather sternly perhaps, to abandon a pair of concepts that were never large enough to begin with. That invitation is not comfortable, but it is intellectually honest. It says that nature is richer than the first categories we formed to manage experience. It says that the invisible is not obliged to look like miniature versions of the visible, and it says that scientific understanding sometimes grows not by sharpening old labels, but by discovering the limits of labeling itself. Still, even after all this, one final question remains waiting in the quiet. If wave and particle are limited names for a deeper quantum reality, then what should we say that reality is? Not merely how it behaves in this or that experiment, but what sort of thing it most fundamentally amounts to. And it is here, right at the edge of that question, that physics becomes most careful. because the theory gives us astonishing power without yet granting a single, universally agreed picture of what lies underneath. That is the threshold we have reached now, where language grows cautious, and the final step is not to choose between two old masks, but to ask what kind of face, if any, was ever behind them at all. So where does all of this leave us? After the slits and the detectors, after light behaving in packets and electrons producing interference, after probability waves and measurement and the strange discipline of uncertainty, what are we actually supposed to say the world is like beneath all those borrowed names? If wave and particle are both useful and both incomplete, then what kind of reality sits underneath them? What is the thing itself, if there is a thing itself, when all the familiar labels have started to loosen in our hands? This is the point in the story where physics becomes both more honest and more cautious. Earlier in the journey, it was still possible to hope that one of the old pictures would eventually win. Perhaps light only looked like a wave in some situations, but would turn out to be particulate underneath. Or perhaps electrons only looked particle-like when measured, and would turn out to be true waves all along. There was comfort in that kind of hope because it suggested the trouble was temporary. It suggested the disagreement was in us, not in the structure of the world. If only we were clever enough, perhaps we would discover the final answer and put the whole business neatly to bed. Quantum physics has not done that. It has given us something stranger and, in its own way, more interesting. It has shown that the most reliable theory we have at these scales does not begin by asking whether a thing is fundamentally a wave or fundamentally a particle. It begins with a state. It begins with a mathematical object that encodes what can be said about a system, how that state changes with time, and what outcomes may occur when different measurements are made. That state is not a classical wave in the old everyday sense, and it is not a classical particle carrying a full set of sharply defined properties through space, whether or not anyone looks. It is something more general than either. This is where many people feel an understandable frustration. A mathematical state does not sound like an answer to the question of what is real. It sounds like a technical move, perhaps even a dodge. It can sound as though physics is saying that instead of telling us what the world is, it will only tell us what we can predict. There is some truth in that complaint, but only some. Physics is indeed at its strongest when it links preparation, evolution, and measurement with precise predictions. But that does not mean it has no view of reality. It means that reality, as described by the theory, may not fit the old visual expectations we carried into the problem. The deeper reality beneath the names may be something whose natural form is mathematical before it is pictorial. That idea can sound cold at first, but I do not think it has to be. Mathematics in physics is not just a bookkeeping exercise. It is a way of tracking patterns that the world genuinely seems to follow. If the quantum state predicts interference, tunneling, atomic structure, spectral lines, chemical bonding, semiconductors, lasers, and all the rest with extraordinary success, then it is not unreasonable to believe that it is latching onto something real, even if our language struggles to say exactly what sort of real it is. The mistake may be in demanding that all reality be visualizable in the style of ordinary objects. One possibility, which many physicists have taken seriously, is that the quantum state itself is real. On this view, the wave function is not just a tool for organizing our knowledge. It is an actual feature of the world, though not one that looks like a lump or a ripple in ordinary space. The world at its base would then be made not of little classical objects with hidden definite properties, but of quantum states evolving according to lawful rules. The definite facts we observe would arise from how those states interact with measurement devices, environments, and one another. This picture has a certain directness to it. It takes the most successful part of the theory and says, yes, that is not merely a trick of our calculations. That is part of what reality is. But even this view comes with complications. If the quantum state is real, then what about collapse? Does the state actually jump when a measurement occurs? If so, what causes that jump, and when exactly does it happen? If not, then how do definite outcomes arise from a state that evolves smoothly and contains multiple possibilities? This is the point where different interpretations begin to part ways. In one family of interpretations, the wave function is real and it does not collapse in the old abrupt sense. Instead, what we call a measurement is just another physical interaction in which the observer and apparatus become entangled with the system. The apparent uniqueness of outcomes arises because observers find themselves in one branch of a larger quantum state, with other branches containing other outcomes. This is the idea often associated with the many worlds interpretation. It is famous, often mocked, occasionally romanticized, and much harder to dismiss than its popularity in science fiction sometimes suggests. On this view, the deeper reality beneath the names is not a world of single classical facts waiting quietly behind the scenes, but a branching quantum structure in which all allowed outcomes occur in different branches of the total state. That is a large idea, and I do not say large only in the numerical sense. It asks us to give up the comfort that one definite outcome was singled out by some extra event called collapse. Instead, it says the quantum state evolves continuously, and the appearance of one outcome arises because observers become part of the branching structure. Many physicists find this elegant because it preserves the mathematical simplicity of the theory. Others find it extravagant because it seems to multiply realities beyond comfort. Either way, it shows how far beyond wave and particle the conversation has gone. We are no longer merely deciding how to label a microscopic object. We are debating the architecture of reality itself. Another family of interpretations takes a different route. It says that the quantum formalism is indeed correct, but the wave function is best understood not as a direct physical substance or field, but as a description of what can be known or expected about a system. In this kind of view, the theory is fundamentally about information, inference, or the rules connecting preparations and observations. The deeper reality may still exist, but quantum mechanics is not necessarily trying to picture it directly. It is instead giving us the framework for predicting measurement results. This has the advantage of avoiding some of the stranger ontological commitments, but it also leaves many people dissatisfied because it seems to retreat from the question of what is there when no one measures. Then there are hidden variable theories, which attempt to restore a deeper level of definiteness beneath the probabilities. In these approaches, the quantum state may be supplemented by additional variables not included in the standard formalism. Those extra elements would determine what actually happens in an individual case, even if the standard theory only gives probabilities. The best-known example is pilot wave theory, associated with Louis de Broglie and later David Bohm. In that picture, particles really do have definite positions, but their motion is guided by a wave that evolves according to the usual quantum rules. There is something attractive about this because it restores a kind of underlying realism and gives a more concrete story about what is happening between measurements. Yet pilot wave theory also comes at a price. It introduces a deeper structure that is not local in the old classical sense. What happens in one place can depend in a subtle way on the configuration elsewhere. That non-locality is not a decorative oddity. It is bound up with the experimental facts of quantum entanglement, which suggests that any attempt to restore a fully classical-style hidden reality runs into trouble. The deeper reality, if hidden variables are part of it, does not look like a collection of independent tiny beads carrying all their own private properties. It still ends up being stranger and more relational than classical intuition would prefer. This brings us to entanglement, which may be one of the clearest clues that the deeper reality beneath the names is not fundamentally built from separate little things with self-contained identities. When two quantum systems become entangled, the state of the whole can be sharply defined even when the parts do not possess independent classical descriptions of the same kind. The correlations between them are stronger and stranger than any ordinary shared recipe could explain. Measure one and the result is connected with what can be found in the other, even when the systems are separated. This does not let messages travel faster than light in the usual practical sense. but it does tell us that the world is not always assembled out of fully independent local pieces. That is an extraordinary lesson. For centuries, common sense and classical physics encouraged the picture of reality as built from objects, each with its own properties, each occupying its own place, each interacting with others through causes that could be traced in space and time. Quantum entanglement does not destroy locality in every sense, but it does show that separability is not as fundamental as we once assumed. The state of the whole can be more basic than the state of the parts. Relations can be primary. In that sense, the deeper reality beneath the names may be less object-based than we had imagined. Some physicists and philosophers have therefore been drawn toward a relational view of quantum mechanics. On such views, the properties of a system are not absolute in the old classical way, but are meaningful only relative to other systems or specific interactions. That may sound unsettling, because it seems to threaten the idea of a shared objective world. But relational approaches do not usually deny objectivity altogether. They suggest instead that objectivity emerges from stable patterns of relation and agreement among systems, not from the possession of all properties by each system in isolation. Once again, the deeper layer appears to be built not from self-standing little entities wearing clear identity cards, but from structured connections and interactions. There is also a more radical possibility, one that has become increasingly important in some areas of theoretical physics. It is the idea that information itself may be closer to fundamental than matter in the old sense. I do not mean information as in email messages, shopping lists, or the number of unread messages on your phone, all of which can be stressful enough without being metaphysically basic. I mean information in the sense of distinctions, correlations, and the structure of what can be known about physical systems. In some approaches to quantum gravity and black hole physics, questions about information become central. What is preserved? What is lost? How is the world structured so that the laws remain consistent? This has led some thinkers to suspect that the deepest layer of reality might be better described in informational or relational terms than in terms of a little material bits moving around in a background stage. If that is right, then wave and particle are even more clearly surface descriptions than we first thought. They would be practical appearances arising from a deeper order of states, correlations, and constraints. A particle would be a particular kind of detectable localized event or excitation. A wave would be a pattern in the structure of possibilities or amplitudes. Neither would be the final furniture. Both would be ways the deeper order becomes legible to creatures like us, equipped with detectors, screens, clocks, and theories. It is worth saying again that none of this means physics has dissolved into philosophy without anchor. The deeper interpretations may be debated, but the experimental backbone remains extremely firm. Interference happens, quantized detections happen, entanglement happens, decoherence happens, quantum statistics work. The unresolved question is not whether the theory connects with reality. It plainly does. The question is what kind of reality can support all these facts at once. That is a very different sort of uncertainty from mere confusion. It is the uncertainty of standing before a structure that is clearly there, clearly lawful, and not yet fully captured by any one intuitive picture. There is something mature, I think, in allowing the answer to remain open where the evidence does not force closure. Science does not become stronger by pretending to know more than it does. It becomes stronger by being precise about where explanation is secure and where interpretation remains contested. Quantum mechanics is secure in its predictions to a degree that would be the envy of nearly any other theory. Its interpretations remain under discussion not because the theory is weak, but because the reality it points toward is more subtle than the concepts that first brought us into the discussion. So what shall we say, finally, about the deeper reality beneath the names? We can say this much. It is not well captured by the old classical categories taken as final. It is not simply a world of tiny particles with hidden definite properties. It is not simply a world of continuous waves in the old everyday sense. It is a world described by quantum states, structured by probabilities, constrained by uncertainty, shaped by superposition, and knit together by entanglement. It is a world in which measurement does not merely reveal, but helps define the form in which outcomes become definite. It is a world where relations matter deeply, where possibilities have structure before facts are recorded, and where the mathematical description seems to reach farther than our inherited visual intuition. That may sound less like an answer than a careful map of where older answers fail. But that in science is often a genuine kind of progress. To learn that a question was too narrow is not to lose understanding. It is to gain a wider frame. The old debate asked whether reality must resemble one familiar image or another. Quantum physics replies that reality is under no such obligation. It gives us phenomena that borrow from both images and exceed them both. It gives us a theory whose deeper meaning is still debated, but whose practical truth is confirmed every time an experiment works exactly as it should. And perhaps that is the quiet lesson underneath all this. The universe is not built to flatter common sense. It is built however it is built, and our job is to follow the evidence far enough that our language changes with it. We began with a question that seemed simple enough to ask at bedtime: wave or particle? We end with something more demanding and more honest. The deepest layer we can presently describe is quantum, and quantum reality does not fit neatly inside the names we first offered it. Those names remain useful, much as maps remain useful, even when they are not the territory itself. But beneath them lies a structure more disciplined, more elusive, and more real than either label on its own. And here, perhaps, is the gentlest way to leave it. Not by pretending the mystery has been exhausted, nor by making it sound as though physics knows nothing, but by noticing what has actually been achieved. We have learned that light and matter do not need to choose between our old categories. We have learned that probability is not the enemy of knowledge. We have learned that measurement is part of the story, not merely a window beside it. We have learned that the invisible has shape, that relations can be fundamental, and that reality may be deeper than the nouns we inherit from daily life. That is not a small thing to discover. It is a change in how the world can be thought. So if you find yourself, after all this, still wanting to ask whether the quantum world is really made of waves or really made of particles, perhaps the most faithful answer is this: it is made of something that gives rise to wave-like and particle-like behavior without being fully reducible to either. And if that feels unsatisfying, it may simply mean you have followed the subject far enough to reach the point where physics becomes most interesting, because that is often where understanding stops feeling like possession and starts feeling like attention.